There is a light in the sky tonight that wants you dead. I don't mean that as a metaphor. I don't mean it as a hook or a bit of gothic flair to get you to keep watching. I mean it in the most literal sense that a sentence can carry. There is, at this exact moment, a bright, calm, silver-white pinprick hanging low over the western horizon, or maybe the eastern one, depending on the time of year and where you're standing. And that pinprick is a machine for killing things. It has been killing things for 4.5 billion years. It killed its own oceans. It killed its own atmosphere. It killed, if it ever existed, its own biosphere. It has killed every human-made object we have ever thrown at it, without exception, and it has killed most of them within minutes of arrival. That light is Venus. And I want to spend the next several hours telling you exactly, precisely, in as much unflinching detail as I can manage, what Venus is. Not the Venus of Roman mythology, not the Venus of Botticelli's painting rising from a scallop shell, not the Venus of astrology columns or perfume advertisements. The real Venus. The one that's out there right now, 40 million kilometers away on a good day, quietly cooking itself at temperatures hot enough to glow. I want to tell you what it would do to you if you went there. I want to tell you what it did to every probe we ever built to visit it. And there have been many, and they have all died. And some of them died in ways that would give a hardened forensic pathologist nightmares. I want to tell you about its volcanoes, which outnumber Earth's by orders of magnitude, and which may, at this very moment, be erupting. I want to tell you about the possibility, still not ruled out despite our best efforts, that something is alive in Venus's clouds. Not something noble or peaceful or curious about us, but something small and desperate, clinging to existence in droplets of concentrated acid, the last refugee of a murdered world. And I want to tell you, at the end, why we're going back. Because we are. 3 separate space agencies right now are building spacecraft to return to Venus in the late 2020s and early 2030s. NASA is sending Da Vinci, a probe that will deliberately plunge into Venus's atmosphere, knowing it will be destroyed. NASA is also sending Veritas, an orbital mapper. Europe is sending Envision. India, Russia, China, and even private companies have Venus missions in various stages of planning. After 40 years of neglect, we are collectively deciding to walk back into the fire. And to understand why, to really understand why anyone would voluntarily send a machine, or possibly one day a human being, into the most hostile environment in our solar system, you first have to understand what that environment actually is. So let me begin with the numbers. Just the numbers. No metaphors yet. No poetry. Just the cold, factual, appalling numbers that describe the surface conditions of Venus. The temperature is 464 degrees Celsius, 867 degrees Fahrenheit. That is hotter than the melting point of lead, hotter than the melting point of tin, zinc, bismuth, cadmium, and thallium, hotter than a self-cleaning oven at its highest setting, hotter than the inside of a working pizza oven by a factor of 2. If you took a standard kitchen oven and cranked it as high as it would go and left it running for a decade, you would still not approach the average temperature at the surface of Venus. The atmospheric pressure is 92 bars. That is 92 times the pressure at sea level on Earth. That is the same pressure you would experience if you dove 900 meters, nearly a kilometer, beneath the ocean's surface. Human beings cannot go 900 meters deep in the ocean. Our submarines, most of them, cannot go 900 meters deep. The pressure at that depth is enough to crush a nuclear submarine's hull. Venus applies this same pressure to every square centimeter of its surface, all the time, everywhere, forever. The atmosphere is 96.5% carbon dioxide. The remaining 3.5% is mostly nitrogen, with trace amounts of sulfur dioxide, argon, water vapor, carbon monoxide, helium, and neon. There is no free oxygen. There is nothing you can breathe. Even if you could somehow survive the heat and the pressure, you would suffocate within seconds of removing whatever life support you'd brought with you. The clouds are made of sulfuric acid, not diluted sulfuric acid, not lightly acidic water, concentrated sulfuric acid, 75 to 96% pure, in the form of droplets and haze that stretch from about 45 kilometers above the surface up to about 70 kilometers. This is battery acid. This is the acid that etches metal, dissolves organic tissue, and burns through skin on contact. And it doesn't stay in the clouds. It rains. Sulfuric acid falls from the sky on Venus, though most of it evaporates back into vapor before it reaches the ground, because the ground is too hot for liquid acid to persist. The winds at the cloud tops move at 360 kilometers per hour. That is faster than a Category 5 hurricane. That is faster than the fastest tornadoes ever recorded on Earth. And these winds don't just show up occasionally. They blow constantly, wrapping the entire planet in a permanent supersonic adjacent gale that circles the globe every 4 Earth days. The day is 243 Earth days long, longer than the Venusian year, which is only 225 Earth days. Venus rotates so slowly that if you stood on its surface, again ignoring for a moment that you would be dead in less than a second, you would experience one sunrise and one sunset every 117 Earth days. You would wait 4 Earth months between meals, if meals were tied to daylight. The concept of morning and evening would lose all meaning. The rotation is backwards. Venus spins the opposite direction from every other major planet in the solar system. If you could stand on Venus and see the sun through the clouds, you can't, but if you could, it would rise in the west and set in the east. The reasons for this backwards rotation are still debated by planetary scientists, and I'll come back to it later, but the leading theory involves an ancient collision so violent that it flipped the entire planet upside down. The surface, when you finally get down to it, is dry stone. No liquid water, not a drop, not a puddle, not a damp patch. Venus once had oceans. We're increasingly sure of this. But every molecule of that water is gone now, either boiled into the sky and torn apart by ultraviolet radiation or lost to space. The surface today is bone-dry basaltic rock, some of it flat plains, some of it mountainous, all of it baked to a uniform glowing hell. These are the numbers. This is the environment. And I want you to understand something about these numbers because they can wash over you if you're not careful. It's easy to hear 464 degrees Celsius and just categorize it as very hot without really internalizing what it means. So let me try to make it concrete. If you took a fully grown, healthy human being and instantly transported them to the surface of Venus, assume magic, no travel time, just a snap of fingers and there they are. Here is what would happen in the first 60 seconds. Before we even get to the heat, they would be crushed. The atmospheric pressure of 92 bars would slam into every part of their body simultaneously, compressing their chest cavity to the point where breathing would be impossible. Not painful, not difficult, impossible. The muscles that expand the rib cage cannot generate enough force to fight 92 atmospheres of external pressure. The lungs would collapse. The eardrums would rupture instantly, not just perforate, but explode inward. The sinuses would fill with blood as capillaries burst under the differential. This would happen within the first second. Simultaneously, the heat would begin its work. At 464 degrees Celsius, the ambient temperature is more than 4 times the boiling point of water at sea level. And remember, this is a pressurized 464 degrees, which means the heat transfers into a body far more efficiently than it would in Earth's thin, cool air. Human skin, which starts to blister at around 45 degrees Celsius and to char at around 200, would begin cooking immediately. But cooking understates it. At Venusian surface conditions, human tissue would not so much burn as render. The outer layers of skin would blacken and split within seconds. Subcutaneous fat would liquefy. Muscle tissue would begin to seize and contract as its proteins denatured, twisting the corpse into the same clenched fetal posture that archaeologists find in the victims of Pompeii. The pugilistic pose, they call it, because the arms come up like a boxer's guard as the biceps and triceps cook and shorten at different rates. But this is not Pompeii. Pompeii's victims died in a pyroclastic flow that reached maybe 300 degrees Celsius for a few seconds. Venus's surface is 464 degrees, constantly, forever, with 92 atmospheres of pressure driving the heat into every crevice of the body simultaneously. Within 10 seconds, the eyes would boil. Not evaporate, boil. The vitreous humor, which is 99% water, would flash into steam inside the eye sockets, and the resulting pressure would rupture the eyeballs outward. But because the ambient pressure is so much higher than the pressure generated by the boiling, the steam couldn't actually escape efficiently, so the eyes would essentially cook in place, in their own vapor, sealed inside skulls that were themselves beginning to superheat. Within 20 seconds, the internal organs would begin failing in sequence. The blood, which is mostly water, would attempt to boil, but couldn't. The external pressure prevents boiling by keeping the water in liquid form, even at extreme temperatures. So instead, the blood would simply cook. Proteins would denature. Hemoglobin would lose its ability to bind oxygen, though this hardly matters because there's no oxygen anyway. The heart, whose muscle fibers require precise electrical timing to function, would fibrillate and stop as its electrolyte balance collapsed under thermal stress. Within 30 seconds, the skeleton would still be intact, but everything soft around it would be partially liquefied and partially charred. The person would no longer resemble a person. They would resemble a burnt roast in the vague shape of a human, sitting in a pool of their own rendered fat, surrounded by acid vapor that hisses as it contacts the cooling grease. Within 60 seconds, chemical breakdown would accelerate. Sulfuric acid, present in trace amounts even at ground level, would begin dissolving what was left of the exposed tissue. The bones, calcium phosphate mostly, would slowly begin to react with atmospheric compounds. Given enough time, days or weeks, the entire body would be reduced to a small pile of mineral residue and a stain on the rock. But nobody would ever see it, because there is no one on Venus. There has never been anyone on Venus. There will not be anyone on Venus for a very long time, if ever. And that is what Venus does to a human being in the first minute. I lay this out in detail. I know it's grim. I know it's a lot. Because I think there is a tendency when we talk about harsh environments in space to blur them all together into a general concept of bad place, don't go. The moon is a harsh environment. Mars is a harsh environment. The vacuum of space is a harsh environment. And in some sense, they all are, but they are not the same. They kill in different ways, on different timescales, with different levels of violence. Vacuum, for instance, is famously not as bad as movies make it out to be. If you were shoved out an airlock without a suit, you would not explode. You would not freeze instantly. You would have about 15 to 30 seconds of useful consciousness before hypoxia knocked you out, and death would follow a couple of minutes later. It would be an unpleasant way to die, but it would be relatively slow, relatively quiet, and relatively survivable if someone got to you quickly enough. People have been briefly exposed to vacuum in industrial accidents and survived with lasting but non-fatal injuries. The moon is worse than vacuum because of the temperature swings and the radiation, but the fundamental problem is the same. It's an empty, cold, low-pressure place, and if you're properly suited up, you can walk around on it. 12 human beings have done exactly that. They came back fine. Mars is worse than the moon because it has weather, dust storms mostly, and violent temperature gradients. But again, with the right suit and habitat, you could survive on Mars. The atmosphere is thin enough that pressure isn't a problem. The temperature is cold enough that you need insulation, but not so cold that it's unmanageable. The radiation is a long-term cancer risk, not an immediate death sentence. Venus is categorically different from any of these. Venus does not require the absence of life support to kill you. Venus kills through the presence of things. Too much heat, too much pressure, too much acid, too much carbon dioxide. It is not a passive environment that you can insulate against with the right equipment. It is an active, aggressive, chemically hostile system that attacks anything you send into it from multiple directions using multiple mechanisms all at once. This is why we have never landed a human being on Venus. This is why we probably never will, at least not on the surface. And this is why every single probe we have ever sent to Venus's surface has died within hours of arriving. Most within minutes, some within seconds. Venus does not tolerate visitors. Venus is not place. Venus is an event, and the event is ongoing, and the event is called destruction. I want to spend some time on the heat specifically, because I think this is the aspect of Venus that most people fail to properly grasp. When you tell someone Venus is hot, they picture a desert. They picture Death Valley. They picture the inside of a car parked in Arizona in July. These are useful comparisons for talking about hot as a human experiences it, but they are useless for talking about Venus. Venus is hot in a way that transcends human experience of hot. Let me start with the number again, 464 degrees Celsius. Now let me put that in industrial context, because industry is the only place on Earth where we routinely deal with these kinds of temperatures. At 464 degrees Celsius, lead melts. Lead's melting point is 327 degrees Celsius. Venus would melt lead into puddles on its surface. If you brought a lead brick to Venus and set it down, it would collapse into a shining silvery pool within minutes. Zinc melts. Zinc's melting point is 419 degrees Celsius. This is important because zinc is used in galvanization, which is how we protect steel from corrosion. On Venus, all galvanized steel would immediately have its protective coating melt off. Tin melts. Tin melts at 232 degrees Celsius. Not only would tin melt on Venus, it would melt more than 230 degrees below the ambient temperature. meaning tin would exist as a superheated liquid, more like liquid mercury than like solid metal. Bismuth, cadmium, thallium, and several other metals all melt. Aluminum does not quite melt. Aluminum melts at 660 degrees Celsius. So aluminum survives on Venus barely, but it becomes soft. Structural aluminum, which is what most spacecraft are built from, would lose most of its strength and rigidity at Venusian temperatures. It would deform under any load. It would sag. It would creep. Solder melts spectacularly. Standard electronic solder melts at around 180 degrees Celsius. Every electronic component in every spacecraft that has ever landed on Venus began falling apart from solder joint failure within the first few minutes of arrival, before the heat had even fully penetrated to the internal circuit boards. Rubber, plastic, and every organic material used in normal engineering becomes gas. There is no polymer known to human materials science that can survive 464 degrees Celsius in a chemically active atmosphere for more than a few minutes. Teflon, one of the toughest polymers we have, decomposes at 400 degrees Celsius. Kevlar goes at about 450 degrees Celsius. Every plastic wire coating, every rubber gasket, every polymer seal in a spacecraft turns into vapor almost immediately upon landing on Venus. Wood ignites. Obviously, but worth stating, paper ignites at 233 degrees Celsius, wood at around 300 degrees Celsius. If you brought a book to Venus, it wouldn't even have time to fall out of your hand before it burst into flame. Except, and this is the horror twist, it wouldn't really burn in the normal sense because there's no oxygen. It would pyrolyze. It would decompose thermally into carbon and volatile organic compounds without the classic flame reaction. So the book would blacken, smoke, and crumble into carbon dust without ever actually burning. Fire, as we understand it, doesn't really work on Venus. Think about that for a second. Venus is hot enough to burn anything, but it lacks the oxygen for actual combustion. So things don't burn on Venus, they just disintegrate thermally, quietly, without flame, in an atmosphere that watches them come apart the way you'd watch ice melt in a warm room. It is the most alien form of destruction I can imagine. A universe where fire itself refuses to appear, but everything is destroyed anyway, by heat alone, silently and without light. Now let me push further because 464 degrees Celsius is only the average surface temperature. Venus has geography. It has mountains and lowlands, and the temperature varies with altitude in ways that are counterintuitive to anyone who grew up on Earth. On Earth, higher altitudes are colder. You climb a mountain, the air thins, the temperature drops. Everyone knows this. Mount Everest has snow at the top, even though it sits near the equator, because at 8,848 meters up, the temperature averages about minus 36 degrees Celsius. On Venus, higher altitudes are also colder, but colder is relative. The highest point on Venus is a peak called Maxwell Montes, which rises about 11 kilometers above the mean surface elevation. At the summit of Maxwell Montes, the temperature is around 380 degrees Celsius. That's still hot enough to melt lead. It's just less hot than the lowlands. And here's where Venus does something that no other place in the solar system does. On the peaks of the tallest Venusian mountains, at that cool 380 degrees Celsius, there is snow. Not water snow, not carbon dioxide snow, like on Mars. Metal snow. The exact composition is still debated, but the leading theories suggest it's some combination of galena, lead sulfide, bismuth sulfide, and tellurium compounds. These metallic compounds evaporate off the hot lowland surfaces as vapor, rise into the atmosphere, cool slightly at higher altitudes, and precipitate out onto the mountaintops as a shining, reflective metallic frost. Radar observations of Maxwell Montes show that the peaks are unusually reflective. They shine in radar wavelengths in a way that plain rock doesn't. Something is coating the top of that mountain, something metallic, something that fell out of the sky. I want you to picture this for a second because I think it's one of the most alien and beautiful and horrifying images in the entire solar system. Somewhere on Venus, there is a mountain. The mountain is 11 kilometers tall, taller than Everest, and it sits on a plain that glows dull red from residual heat. The sky above is a heavy, orange, opaque haze, thick with sulfuric acid clouds that never part. There's no visible sun. There's no wind at the surface because the atmosphere is so dense that surface winds only crawl at a few kilometers per hour, despite the raging super rotation up in the clouds. And on top of that mountain, in the perpetual twilight of Venus's atmosphere, there is a coating of metallic frost, lead frost, bismuth frost, a shining silver gray dusting on the summit of a mountain that no human eye will ever see directly. That is the Venus we don't talk about enough. The heat also does something to the appearance of Venus's surface that is worth pausing on. Because at 464 degrees Celsius, rock does not glow with white-hot brilliance the way it does at, say, 1000 degrees Celsius, but it does glow dimly. The lowland plains of Venus emit their own infrared radiation and enough visible red light that if you were somehow standing there, again, ignoring the immediate death, the ground beneath your feet would be faintly luminous. A dull, sullen, red-orange glow, like the last coals of a dying fire, spread out across an entire planet. Everything glows. The rocks glow. The dust glows. The mountains glow less brightly at higher altitudes because they're cooler. Any object you brought with you would begin glowing within seconds of arrival as it heated to match its surroundings. Your spacecraft would glow. Your spacesuit before it failed would glow. Your body after it cooked would glow. Venus is a self-illuminating hell. It generates its own faint light from below. The sun, when it filters weakly through the clouds, adds only a slight orange tint to what is already there. The dominant light source on the Venusian surface is the surface itself, radiating away the heat that has been beating into it for 4.5 billion years. There is a specific technical term for how heat moves through Venus's atmosphere, and it's worth explaining because it's part of why Venus is so much more lethal than a hot planet has any right to be. On Earth, when you stand next to a fire, most of the heat reaches you through radiation, infrared photons streaming off the flames. A smaller amount reaches you through convection, hot air rising past your body. On Venus, both mechanisms are cranked up to unprecedented levels. The atmosphere is so thick, 92 times Earth's, that convective heat transfer is enormously efficient. Hot air molecules pack so densely against your skin or your spacecraft's hull that heat pours into you at rates comparable to sticking your hand into an oven full of hot water rather than hot air. Water conducts heat about 25 times better than air. Venusian air, being so compressed, behaves less like Earth's air and more like a hot fluid. It's been described as supercritical or near supercritical, meaning it exists in a state that blurs the line between gas and liquid. At the surface, the CO2 is so compressed that it's technically no longer really a gas. It's a supercritical fluid, the same state that industrial processes use to decaffeinate coffee or extract essential oils, because supercritical CO2 dissolves things beautifully. It penetrates. It seeps into every crack and pore. It carries heat like a liquid, but flows like a gas. Any spacecraft that lands on Venus is not so much sitting in a hot atmosphere as it is immersed in a hot, aggressive, penetrating chemical solvent that pours heat into every surface simultaneously and seeps through every seal. This is why probes to Venus die so quickly. It isn't just the ambient temperature, it's the rate of heat transfer into the probe from the surrounding supercritical CO2. A landed probe cannot lose heat to its environment because the environment is hotter than the probe. So all the heat that pours in, and it pours in fast, accumulates inside the spacecraft. The interior temperature climbs relentlessly, and every component in that interior has a maximum survivable temperature. Some go at 100 degrees Celsius, some at 150, some at 200. As each threshold is passed, another system fails, until finally there's nothing left functioning and the probe goes silent. The best a probe can do is delay its death. It cannot prevent it. Every Venera lander, every Vega descent module, every probe human have ever sent to Venus's surface has died from thermal soak. The heat gets in eventually. It always gets in. The only question is how long you can hold it off. The Soviets built the toughest probes anyone has ever built for this purpose. Their Venera landers were essentially pressure vessels made of titanium, packed with lithium nitrate trihydrate, a phase change material that absorbs heat by melting, surrounded by thermal insulation, refrigerated to sub-zero temperatures before landing, and sealed like submarines. Even so, the longest surviving Venera lander lasted 127 minutes on the surface before it died. 2 hours. That was the record. And it took the resources of a superpower and decades of engineering iteration to achieve. For comparison, the Mars rovers have operated on Mars for years. Curiosity has been active since 2012. Opportunity lasted 15 years. Venus doesn't give you years. Venus doesn't give you months. Venus doesn't give you weeks. Venus gives you, at absolute best, 2 hours, and then it eats your machine. Let me now talk about pressure, because heat is only half the story of Venus's surface. The other half is the crushing, ceaseless weight of that atmosphere. 92 bars. 92 times the pressure at sea level on Earth. I said this earlier, and I want to unpack it now, because pressure is one of those physical concepts that people intuitively underestimate. We deal with atmospheric pressure every day, and we don't feel it because our bodies are pressurized from within to match. We don't notice the roughly 10,000 kilograms of air pressing down on our shoulders at any given moment because an equal amount of pressure is pushing outward from inside us. It's all balanced. It's fine. But change the balance, even a little, and things go wrong fast. A scuba diver who ascends too quickly can suffer decompression sickness, the bends, from as little as a 2-atmosphere pressure change. A commercial diver working at 30 meters depth, 4 atmospheres, requires hours of controlled decompression to surface safely. The deepest untethered scuba dive ever recorded was about 330 meters, or 34 atmospheres, and the diver nearly died. Venus's surface pressure is 92 atmospheres. That is deeper, in pressure equivalent terms, than any human has ever gone underwater. That is deeper than most of our military submarines can operate. That is a pressure environment that, On Earth, we associate only with the deep ocean, with industrial hydraulic systems, and with the interiors of high-pressure chemical reactors. Let me give you some concrete comparisons. The USS Thresher, an American nuclear submarine, was lost in 1963 when it exceeded its crush depth. When the Thresher imploded, it was at approximately 730 meters depth, about 73 atmospheres of pressure. The implosion took less than a tenth of a second. All 129 men aboard died before their nervous systems could register that anything had gone wrong. Investigators later determined that the entire submarine was compressed to a fraction of its original size and reduced to fragments within milliseconds. The energy released by the sudden collapse was roughly equivalent to a small explosion. Venus's surface pressure is higher than the pressure that imploded the Thresher. If you built a nuclear submarine and dropped it on Venus, the submarine would fail catastrophically before it even got to worry about the heat. The Titan submersible, which imploded in 2023 while attempting to reach the wreck of the Titanic, was at approximately 380 atmospheres when it failed. So Venus's surface pressure is less than the pressure that destroyed the Titan. Venus is only 92 atmospheres, while Titanic depth is around 380. In that sense, Venus is survivable in a way the deep ocean is not. But that comparison is deceptive because Venus's 92 atmospheres are 92 atmospheres of hot supercritical CO2, not cold liquid water. The pressure alone is manageable with the right engineering. The Soviets proved this, but the pressure combined with the heat, combined with the chemistry, combined with the acid, combined with the sheer duration required to accomplish anything useful, is what makes Venus's surface such an engineering nightmare. A pressure vessel that can hold back 92 bars is not hard to build. Any decent boiler manufacturer can make one. A pressure vessel that can hold back 92 bars while being cooked at 464 degrees Celsius from the outside is significantly harder. A pressure vessel that can do that and keep sensitive electronics functional inside it and provide viewing ports for cameras and survive the chemical attack of hot supercritical CO2 on its exterior surfaces and do all of this for more than a few hours. That requires materials and design approaches that push the limits of what human engineering can currently achieve. The Venera landers used titanium hulls. Titanium is strong, corrosion resistant, and holds its strength at high temperatures better than steel or aluminum. But even titanium creeps at Venusian temperatures, meaning over time, under sustained load, it slowly deforms. A titanium sphere sitting on Venus's surface would slowly go out of round, its walls slowly thinning at the stress points, its seams slowly working themselves loose. Given enough time, the sphere would fail even without any other damage, simply from being there. Nothing we build lasts on Venus, not because Venus attacks it with any single overwhelming force, but because Venus attacks it with everything, patiently, continuously, from every direction, until the accumulated stresses find a weak point and win. There is a specific kind of horror in this that I want to name. Most hostile environments in the solar system kill you through a single mechanism. Vacuum kills through decompression. Radiation kills through cellular damage. Cold kills through hypothermia. Each is bad, but each is one thing. And if you can solve for that one thing, you can survive. Venus doesn't work like that. Venus kills through multiple simultaneous mechanisms, each of which reinforces the others. The heat weakens materials. The pressure exploits the weakened materials. The chemistry corrodes the surviving materials. The corrosion creates new weak points, which the pressure exploits, which the heat accelerates. It is a self-reinforcing cycle of destruction. Every surface, every seal, every joint, every wire, every lens, every antenna is under attack from 4 or 5 different directions at once. Solve any one of them and the others still get you. This is why Venus is, in my personal opinion, and I'll defend this claim to anyone who wants to argue it, the most hostile environment in the entire solar system. More hostile than the deep atmosphere of Jupiter, where at least the pressure and temperature are somewhat predictable and the chemistry is inert. More hostile than the surface of Io, Jupiter's volcanic moon, where at least you can hide from the radiation and volcanoes in specific safe zones. More hostile than the surface of the Sun, which will never send anything to anyway, but which at least has the courtesy to destroy your spacecraft cleanly and instantly rather than dragging it out. Venus takes its time. Venus makes you watch. Now let me talk about the chemistry, because I've been mentioning sulfuric acid, and I don't think most people appreciate what it means for an entire planet's cloud layer to be made of the stuff. Sulfuric acid, H2SO4, is one of the most industrially important and biologically destructive substances that human civilization uses. It is the workhorse of the chemical industry. We use it to make fertilizer, to refine petroleum, to process metals, to manufacture batteries, to synthesize thousands of other chemicals. It is produced in enormous quantities, over 250 million metric tons per year globally, and it is treated in every industrial context as extraordinarily dangerous. When concentrated sulfuric acid contacts human skin, it does not simply burn in the way a hot object burns. It performs 3 simultaneous chemical attacks. First, it dehydrates the tissue, ripping water molecules out of organic compounds so violently that the released heat causes local scorching. Second, it hydrolyzes proteins, breaking peptide bonds and reducing muscle and skin to a black tarry residue. Third, it oxidizes what's left, converting organic carbon into carbon dioxide and water vapor. The result of a concentrated sulfuric acid exposure on skin is not a burn in the ordinary sense. It is a dissolution. The affected tissue turns black almost instantly, then dark brown, then begins to liquefy at the edges. The characteristic sign of a sulfuric acid injury is a black eschar, a leathery carbonized crust, surrounded by tissue that is chemically being taken apart, molecule by molecule. Industrial safety guidelines classify concentrated sulfuric acid as immediately dangerous to life and health at concentrations above 15 milligrams per cubic meter of air. That's about 15 parts per billion. Venus's cloud layer is roughly 75 to 96% sulfuric acid by concentration. We are not talking about parts per billion. We are talking about clouds that are essentially pure acid hanging in the sky, kilometers thick, spanning an entire planet. If you were dropped naked into Venus's cloud layer at 55 kilometers altitude, the layer where the pressure and temperature are actually similar to Earth's surface, more on that in a bit, the heat would not kill you. The pressure would not kill you. The acid would kill you, and it would take its time about it, and you would be conscious for a lot of it. Your exposed skin would begin to blacken within seconds of contact with the acid droplets. Your eyes would burn immediately upon exposure. The tears, being watery, would react violently with the acid, generating heat and dissolving the corneal tissue in a chemical reaction that would take place inside your eyeballs. You would be blind within seconds. But you would be blind and screaming because the pain of concentrated sulfuric acid on nerve endings is, by all accounts of survivors of industrial accidents, among the most excruciating sensations that human beings are capable of experiencing. You would inhale the acid vapor with your first breath. It would coat the inside of your nose, your throat, your bronchi, your lungs. The mucous membranes would react instantly, dissolving into a bloody froth. You would drown in your own liquefying respiratory tract within a minute or two, unable to see, unable to scream any longer, unable to do anything but feel yourself coming apart from the inside. And this horror, is what Venus's atmosphere is made of, from 45 kilometers above the surface up to 70 kilometers. A 25-kilometer thick layer of concentrated sulfuric acid wrapping the entire planet, permanent, endless. Now, here's the twist. Here is the strange, dark, tantalizing thing that keeps astrobiologists up at night. That acid layer is where the most Earth-like conditions on Venus exist. If life exists on Venus today, and I'll get to whether it might later in painful detail, it lives in the acid clouds. Because paradoxically, the acid clouds are the only survivable region on the entire planet. The surface is too hot, too pressurized, too dry. The upper atmosphere is too cold, too thin, too irradiated. But in a narrow band centered around 50 to 55 kilometers altitude, the temperature is between about 30 and 70 degrees Celsius, and the pressure is about 1 Earth atmosphere. Humans could survive there in a light suit and a breathing mask. Barring the acid, of course, which is unbearable. Life, Earth life at any rate, cannot tolerate concentrated sulfuric acid. Not human life, not bacterial life, not any life we know of. There are extremophiles on Earth that thrive in mildly acidic conditions, in geothermal vents and mine tailings, but even the toughest of them, organisms like Picrophilus territus that live at pH 0, are dealing with dilute acid environments. They cannot survive in 90+% sulfuric acid. Nothing from Earth can. And yet, there is something in Venus's cloud that we do not fully understand. There are dark streaks visible in ultraviolet imagery, bands of material that absorb UV light in patterns that don't match any known atmospheric chemistry. Nobody knows what those UV absorbers are. They have been observed for over 60 years, since the earliest ground-based ultraviolet observations of Venus in the 1920s, and their composition remains, as of this recording, unidentified. Various compounds have been proposed: sulfur allotropes, iron chloride, various organic molecules, but no proposal has fit the observations perfectly. Some scientists, a minority but a growing one, have suggested that the UV absorbers might be biological, that the dark streaks in Venus's clouds might be populations of something, microorganisms perhaps, riding the acid droplets, using ultraviolet light as an energy source, doing whatever equivalent of photosynthesis their strange chemistry allows. This is speculation. It is not proven. It is not even really a mainstream hypothesis. But it is a hypothesis that cannot be ruled out with current data. And when a hypothesis about extraterrestrial life cannot be ruled out with current data, it deserves attention, because the alternative, that we have been staring at biosignatures for a century without realizing it, is exactly the kind of failure that history judges harshly. I will return to the possibility of Venusian life in much more detail later. For now, I want to plant the flag. The acid clouds are horrifying, and the acid clouds might also be inhabited. Both of these can be true at once. Neither excludes the other. Let me now tell you the story of every spacecraft we have ever sent to Venus, in order with attention to how each one died. This is not a happy list. This is not a triumph of exploration. This is a catalog of destruction. The story begins in 1961. Venera 1, 1961, Silent Death. The Soviet Union launched Venera 1 on February 12, 1961. It was the first spacecraft ever intended to reach another planet. It weighed 643 kilograms. It carried instruments to measure cosmic rays, micrometeoroids, magnetic fields, and solar wind. It was supposed to fly past Venus and send data. 7 days after launch, at a distance of about 2 million kilometers from Earth, Venera 1 stopped responding. Its onboard systems failed for reasons that were never definitively determined. The spacecraft continued on its trajectory in silence, passed within 100,000 kilometers of Venus on May 19, 1961, and vanished into the darkness of interplanetary space, mute and dead. It was not destroyed by Venus. It never got close enough. But it set the tone for what was coming. Mariner 1, 1962, suicide by punctuation. The United States tried next. Mariner 1 launched on July 22, 1962, bound for a Venus flyby. Less than 5 minutes after launch, the rocket veered off course and had to be destroyed by range safety officers before it could crash into an inhabited area. The subsequent investigation determined that the failure was caused by a missing hyphen in the guidance software, a single character omitted from a mathematical formula, which caused the rocket to interpret normal variations in velocity as catastrophic errors and attempt to correct for them, sending it out of control. Venus 1, Earth 0, and Venus hadn't even done anything. Mariner 2, 1962. The first success, sort of Mariner 2, launched a month later and became the first spacecraft to successfully fly past another planet. On December 14, 1962, it passed within 34,833 kilometers of Venus and returned data on the planet's temperature, atmospheric composition, and magnetic field. It was Mariner 2 that first confirmed, to the shock and disappointment of everyone who had been imagining Venus as a jungle-covered sister world, that the planet's surface was hot enough to melt lead. Mariner 2 survived. It didn't land, though. It just flew by. Venus doesn't kill flyby missions because flyby missions don't come close enough. The killing zone begins when you try to actually go there. Zond 1, 1964. Slow suffocation. The Soviets launched Zond 1 in April 1964. Its mission was to fly past Venus and study its environment. Almost immediately, the spacecraft developed a leak in its pressurized instrument compartment. Nitrogen gas seeped out into the vacuum of space, slowly at first, then faster as seals degraded. Ground controllers watched helplessly as their spacecraft died over the course of weeks. They managed to maintain contact until mid-May, when the transmitter finally failed. Zond 1 continued on its trajectory, passed within 100,000 kilometers of Venus on July 14, 1964, and became another silent metal corpse tumbling through the solar system. Venera 2, 1965, overheated Venera 2 was launched in November 1965. It was designed to fly close to Venus and take photographs. It got very close, about 24,000 kilometers, on February 27, 1966. But during the approach, its onboard systems overheated, likely due to a combination of solar heating and inadequate thermal management. All communications ceased. Venera 2 flew past Venus in silence, having taken no useful data, having transmitted nothing to Earth. The Sun killed it, technically not Venus. But the mission profile was Venus's fault. Venera 3, 1966, the first corpse. Venera 3, launched at the same time as Venera 2, achieved something historic. On March 1st, 1966, it became the first human-made object to impact the surface of another planet. Impact, not landing. Impact. The spacecraft had lost communication before atmospheric entry, so nobody on Earth received any data from the descent. The parachute may or may not have deployed. The landing capsule may or may not have survived entry. What we know for certain is that a Soviet-built metal object, roughly the size and shape of a beach ball, slammed into the surface of Venus somewhere on the night side of the planet and became the first piece of Earth-manufactured hardware to be destroyed by Venus's environment. We don't know exactly how it died. We don't know if it was crushed by the pressure, cooked by the heat, or shattered by impact. All three, probably, in some sequence. What we know is that it is still there, somewhere, a lump of ruined titanium and steel sitting on Venus's surface, being slowly dissolved by the atmosphere over the course of geological time. Venera 3 was the first of many. The Venusian graveyard had officially opened for business. Venera 4, 1967. Crushed from above. Venera 4 was the first spacecraft to successfully transmit data from within another planet's atmosphere. It arrived at Venus on October 18, 1967, and released a descent probe that entered the atmosphere and began sending back measurements. The probe was designed to withstand pressures up to 25 atmospheres, because Soviet engineers, based on the best data available at the time, believed that was roughly the surface pressure of Venus. They were wrong. The actual surface pressure was 92 atmospheres, nearly 4 times what they had planned for. Venera 4 descended into the atmosphere, transmitting temperature and pressure data as it went. The temperature climbed steadily. The pressure climbed steadily. Then, at about 25 kilometers altitude, at a measured pressure of 22 atmospheres and a temperature of about 270 degrees Celsius, the probe's transmissions abruptly stopped. Soviet engineers initially believed the probe had reached the surface and been destroyed on landing. Later analysis incorporating data from subsequent missions that revealed the true surface pressure showed the truth. Venera 4 had not reached the surface. It had been crushed by atmospheric pressure at an altitude of 25 kilometers, still 25 kilometers above the ground, and its wreckage had continued falling, passively, silently, dead, for another 25 kilometers through hotter and denser air, arriving at the surface as a mangled sphere of broken titanium that no longer transmitted anything to anyone. The atmosphere had eaten it in the air. It never even got to try landing. The pressure at altitude was enough. This was Venus's first great lesson to Soviet engineers. Whatever you think this planet is, whatever your best models say, whatever your instruments back home have told you, you are underestimating it. Venera 5 and Venera 6, 1969, crushed together. The Soviets came back in 1969 with 2 probes launched 5 days apart, designed to arrive at Venus within a day of each other. Venera 5 and Venera 6 were essentially identical, reinforced versions of Venera 4, built to withstand pressures up to 27 atmospheres. Still not enough. Venera 5 entered the atmosphere on May 16, 1969, deployed its parachute and began transmitting. It transmitted for 53 minutes as it descended. Then it was crushed at an altitude of approximately 18 kilometers at a measured pressure of about 27 atmospheres. Its wreckage fell the remaining 18 kilometers to the surface in silence. Venera 6 arrived the next day, May 17, 1969. It transmitted for 51 minutes. It was crushed at 10 to 12 kilometers altitude, again at about 27 atmospheres of pressure. Its wreckage joined Venera 5s on the surface, adding to the accumulating Soviet debris field. 2 more probes, 2 more corpses, and Venus still hadn't let anyone reach the ground alive. Venera 7, 1970, the first to land, barely the Soviets, now understanding what they were dealing with, built Venera 7 to withstand 180 atmospheres. Twice what the surface pressure actually was. Overkill by design because they were tired of losing probes. Venera 7 launched in August 1970 and arrived at Venus on December 15, 1970. It deployed its parachute at high altitude and began descending. 29 minutes into the descent, the parachute tore. This was almost certainly due to the extreme thermal and mechanical stresses of Venus's atmosphere. Parachute materials do not enjoy being 400 plus degrees Celsius while under aerodynamic load. The probe fell the rest of the way essentially in free fall, tumbling through increasingly dense atmosphere. When it hit the ground, it hit hard, an impact velocity of about 17 meters per second, which for a rigid metal sphere is like being dropped from a 5-story building. It bounced. It rolled onto its side. Its antenna, designed to point up toward Earth, was now pointing sideways. For nearly a full minute, ground controllers received nothing. They assumed the probe was dead. They began writing their post-mortem reports. Then, 23 minutes after impact, a very faint signal appeared. The probe was still alive. It was transmitting from its sideways position, its signal dramatically attenuated by the incorrect antenna orientation, but it was alive, and it was on the surface of Venus, and it was transmitting. For 20 more minutes, it sent back data. A single weak channel of temperature readings, showing 475 degrees Celsius, and a single weak channel of pressure readings, showing 90 atmospheres. Then it went silent forever. Venera 7 was the first spacecraft to survive a landing on another planet. It survived for a total of approximately 23 minutes on the surface of Venus. Then Venus killed it, the way Venus kills everything. But 23 minutes was a victory. A tiny, agonized sideways victory transmitted over a bad antenna from a bouncing corpse. It was enough. Venera 8, 1972, successful doomed Venera 8 arrived at Venus on July 22, 1972, and made a proper soft landing this time. Its parachute held. Its antenna pointed the correct direction. It touched down on the sunlit side of Venus and began transmitting a clean signal to Earth. Venera 8 survived on the surface for 50 minutes and 11 seconds before its systems failed from the heat. During that time, it measured light levels, wind speeds, atmospheric composition, and surface density. It reported that the ground was, in composition, similar to granite, an unexpected finding that suggested Venus might have had liquid water in its distant past, since granite requires water to form. Then the heat killed it, as it always does. The interior of the probe, insulated as it was, could only absorb so much thermal energy before critical components failed. At the 50-minute mark, the signal cut off cleanly. Venera 8 joined its predecessors as a piece of hot, silent scrap on the Venusian surface. Venera 9, 1975. The first photographs. Venera 9 landed on October 22, 1975, and became the first spacecraft ever to transmit photographs from the surface of another planet. Think about that. Photographs from the surface of Venus 50 years ago. This is one of the great underappreciated achievements of the space age, and hardly anyone remembers it. The photographs, there were two, showed a rocky, flat landscape strewn with sharp-edged stones. The lighting was surprisingly bright. The Soviets had expected Venus's surface to be pitch dark, given the thick cloud layer, but it turned out that enough light filtered through the acid clouds to allow photography. The scene was described by one Soviet scientist as looking like a normal rocky desert, but on a planet where the sky is orange and the rocks are the temperature of a broiler. Venera 9 lasted 53 minutes on the surface before dying. Venera 10, 1975, more photos, more death. Venera 10 landed 3 days after Venera 9 on October 25, 1975. It transmitted photographs of a smoother, more weathered landscape, suggesting older terrain. It survived for 65 minutes before Venus killed it. Both Venera 9 and Venera 10 were built with active refrigeration systems, actual chillers, powered by their descent stage batteries, designed to maintain internal temperature survivable for the electronics. This is why they lasted longer than earlier probes. They were, in effect, small submarines with air conditioning, dropped into an environment that treated them as an insult to be corrected. The air conditioning bought them an hour. Then the batteries died, and the coolant boiled, and Venus finished the job. Venera 11 and Venera 12, 1978, cameras broken Venera 11 and Venera 12 landed in December 1978. Both survived their landings. Both transmitted data for over 90 minutes. Venera 12 lasted 110 minutes, one of the longest surface operations ever achieved, but both of them had their cameras fail. The lens caps, which were supposed to eject automatically after landing, did not eject, or the cameras themselves were damaged during descent. The exact cause is disputed. What is certain is that despite 2 successful landings, we got no new photographs from these missions. The engineers who designed those camera systems must have watched the data come back. Pressure, temperature, wind, chemistry, all working, and known that the one thing they most wanted, the visual confirmation, had been denied. And by the time they diagnosed the problem, the probes were dead. There was no fixing it in the field. Venus doesn't allow field service. Venus doesn't allow second attempts. You get one shot, and if your lens caps don't pop, that's your mission. Done. Over. No do-overs. Venera 13, 1982, the best landing ever. Venera 13 is, in my personal opinion, the most successful Venus landing in history. It arrived on March 1st, 1982, and everything worked. The parachute deployed, the lens caps ejected, the soil sampling arm functioned, the X-ray fluorescence spectrometer analyzed the soil composition, the cameras transmitted color photographs, actual color photographs of the surface of Venus, showing a landscape of flat rocks and dark soil under an orange sky. Venera 13 was designed to survive for 32 minutes on the surface. It actually survived for 127 minutes. More than 4 times its design life. It transmitted continuously the entire time, sending back some of the most detailed data about Venus's surface that we have ever obtained. The photographs are extraordinary. You can find them online. I encourage you to look at them at some point after finishing this. They show what appears to be a paved patio somewhere. Flat, tessellated slabs of rock, some cracked, some intact, extending to a strangely close horizon under a hazy sky. There is a piece of the probe visible in the frame, a scalloped landing ring, coated already in a fine dust from the soil sampling operation. The colors are muted, ochre and gray, but they are real colors, and they are of a place, and the place is another planet, and it wants to kill you. 2 hours and 7 minutes. Then Venera 13 died, and its signal cut off, and Venus added another corpse to the collection. Venera 14, 1982. The Cursed Lens Cap. Venera 14 landed 4 days later, on March 5, 1982. It too transmitted color photographs and soil analysis. It too survived for over an hour on the surface, 57 minutes in fact, before the heat finished it off. But Venera 14 has one small tragicomic footnote in the history of space exploration. When it deployed its mechanical soil compressibility probe, an arm designed to punch into the ground and measure how easily the soil deformed, the arm swung out and landed directly on top of the ejected camera lens cap, which had fallen a few centimeters away from the spacecraft. The probe dutifully measured the compressibility of its own lens cap. There is a data point in the historical record, transmitted from the surface of Venus in 1982, that represents the mechanical properties of a small piece of Soviet-manufactured metal sitting on a rock, being poked by a spring-loaded arm that had traveled 40 million kilometers to poke exactly the wrong thing. Venus, in its way, made sure that even our successes came home with a little bit of embarrassment attached. Venera 15 and Venera 16, 1983. Orbiters. Safe Venera 15 and 16 were orbiters, not landers. They mapped Venus's northern hemisphere with radar imaging. They survived because they never descended into the atmosphere. Venus doesn't kill orbiters generally, it just kills anything that tries to enter it. Vega 1 and Vega 2, 1985. Balloons in the acid. The Vega missions were a Soviet-French collaboration, and they did something unprecedented. They deployed balloons into Venus's atmosphere. Each of the two Vega spacecraft, en route to Halley's Comet, dropped a landing package into Venus's atmosphere. Each package contained a lander that descended to the surface and, separately, a helium balloon that inflated at 54 kilometers altitude in the middle of the acid cloud layer and floated there. The balloons drifted with Venus's supersonic winds for approximately 46 hours each before their batteries ran out. They transmitted data on wind speed, temperature, pressure, and atmospheric composition throughout their flight. They confirmed that the cloud-level winds are ferocious, that turbulence is significant, and that the atmospheric chemistry is even more complex than expected. The balloons themselves were made of a special Teflon-based fabric designed to resist sulfuric acid. They held together for the duration of their missions. Then, when their batteries died, they simply drifted, deflating slowly until they descended into the hotter lower atmosphere and were destroyed. 2 balloons, 46 hours each, almost 4 days of atmospheric science, floating in acid clouds on another world. That is one of the strangest and most beautiful achievements in the history of exploration. And it, too, is almost forgotten now. The Vega landers, meanwhile, did their job, soil analysis, atmospheric sampling, and died on schedule, cooked and crushed like all their predecessors. Vega 2's lander survived for 56 minutes. Vega 1's lander was less lucky. A mechanical shock during descent triggered its soil sampling arm prematurely, and by the time it landed, the arm had already done its dance in mid-air over the wrong altitude. It landed, transmitted for a while, and died without ever measuring the soil it was sitting on. The last Soviet-era landing on Venus was Vega 2 in 1985. Since then, for 40 years, no human-built object has touched the surface of Venus. The Venusian graveyard has been quiet. Its dead lie undisturbed under the orange sky, slowly weathering, slowly being consumed by the atmosphere that killed them. The American contribution, Pioneer Venus and Magellan America's approach to Venus, has been mostly indirect. We sent orbiters, not landers. Pioneer Venus 1, launched in 1978, was an orbiter that studied Venus's atmosphere and clouds from safe distance for 14 years, from 1978 to 1992. When its orbit finally decayed, it burned up in Venus's atmosphere. A controlled death, not a landing attempt. Pioneer Venus 2, launched the same year, was a multi-probe mission that released 4 atmospheric probes into Venus's atmosphere in December 1978. None were designed to survive landing, though one, the so-called day probe, did unexpectedly survive impact and transmitted for 67 minutes from the surface before dying. This makes it the only American spacecraft ever to operate on Venus's surface. Magellan, launched in 1989, was the workhorse. From 1990 to 1994, Magellan orbited Venus and used synthetic aperture radar to produce a global map of the planet's surface at unprecedented resolution. 98% of Venus's surface was mapped by Magellan. Every image we have of Venus's global topography, the mountains, the impact craters, the volcanoes, the vast plains, the strange coronae, comes from Magellan's radar. When Magellan's mission ended in 1994, controllers deliberately deorbited it, sending it plunging into Venus's atmosphere. It burned up. It was the last dedicated American mission to Venus, and it has been 30+ years since anything else was sent. The European and Japanese contributions. The European Space Agency's Venus Express orbited Venus from 2006 to 2014. It studied the atmosphere, detected lightning, mapped surface temperatures, and hunted for signs of active volcanism. It ended its mission the same way Magellan did, by plunging into the atmosphere for a controlled destruction. Japan's Akatsuki mission, launched in 2010, initially failed to enter Venus orbit due to a thruster malfunction. It drifted in solar orbit for 5 years, and then Japanese engineers, in a feat of extraordinary improvisation, successfully re-attempted the orbit insertion in 2015 using the spacecraft's small attitude control thrusters. Akatsuki has been in Venus orbit since then, studying the atmospheric dynamics. That is the current state of the art. One orbiter, Japanese, currently at Venus. Nothing else. 40+ years of Venus surface silence. A dead planet in every operational sense from Earth's perspective. But that is about to change. And I'll get to that. We now need to talk about why. Why is Venus like this? What happened? Because here is the strangest, most important, most unsettling thing about Venus. It was not always this way. Venus is, by mass, by size, by density, by composition, and by position in the solar system, Earth's closest twin. It is 95% the diameter of Earth. It is 82% the mass of Earth. It formed from the same disk of dust and gas, from the same starting materials, at roughly the same time, 4.5 billion years ago. In the early solar system, Venus and Earth would have looked to any external observer like siblings. They may have been indistinguishable. Both had oceans. This is now the mainstream view among planetary scientists, and it is supported by multiple lines of evidence. In the early solar system, Venus almost certainly had liquid water on its surface, possibly for 2 billion years or more. possibly longer than Earth has had its oceans, possibly with a stable climate, moderate temperatures, and, for all we know, the conditions necessary for life to arise. Then something went wrong, not quickly, not in a single event. Over the course of hundreds of millions of years, gradually Venus's climate spiraled out of control, and by the time the spiral finished, the planet was a hell world. The mechanism has a name: the runaway greenhouse effect. Here's how it works in the most direct terms I can offer. Venus is closer to the Sun than Earth, about 30% closer. That means it receives about twice the solar energy per square meter that Earth does. This is more sunlight than Earth's climate would tolerate. If Earth were suddenly moved to Venus's orbit, our oceans would begin evaporating faster than they could rain back down, and our climate would begin to shift. For a long time, possibly 2 billion years, Venus's early atmosphere, oceans, and rock cycle managed to compensate for the extra solar heat. Water evaporated, formed clouds, reflected some sunlight back to space, and moderated the temperature. Volcanic CO2 was absorbed by the oceans and locked into carbonate rocks. The system was in balance, or close to it. But that balance was fragile. As the young sun gradually brightened over billions of years, a normal process for main sequence stars, Venus's climate slowly warmed. More water evaporated, more water vapor entered the atmosphere. And here is the crucial fact that people almost always miss when they think about greenhouse gases. Water vapor is itself a greenhouse gas, a powerful one. Much more powerful molecule for molecule than carbon dioxide. So the extra water vapor trapped more heat. The extra heat evaporated more water. The extra water trapped more heat. And a feedback loop began. Slow at first, then faster. At some point, Venus crossed a threshold. Climate scientists call it the moist greenhouse threshold, beyond which the atmospheric water vapor content becomes self-sustaining. Beyond that threshold, the oceans cannot recover. Every drop of water that evaporates makes it harder for water to condense again. The atmosphere becomes so hot and so saturated with water vapor that it can no longer form clouds efficiently. The temperature climbs, the oceans shrink, and still the loop continues. Once the oceans were mostly evaporated, a second thing happened. Water vapor in the upper atmosphere encounters ultraviolet radiation from the sun. UV photons have enough energy to break water molecules apart into hydrogen and oxygen. This process is called photodissociation, and it happens continuously in any atmosphere that contains water vapor. On Earth, this doesn't cause much trouble because Earth has a magnetic field that traps most of the photodissociated hydrogen before it can escape, and because most of Earth's water is safely tucked away in oceans rather than floating in the upper atmosphere where UV can reach it. Venus had no such protection. Venus does not have a strong magnetic field. Venus rotates too slowly to generate one. A Venusian day is 243 Earth days long, longer than a Venusian year, which is only 225 Earth days. Without a magnetic field and without oceans, all of Venus's water was exposed to solar UV, and the resulting hydrogen escaped into space. Over hundreds of millions of years, Venus lost its water, not to space entirely. Some of the oxygen would have combined with surface rocks or been consumed by chemical weathering, but the hydrogen, which is the light half of water, drifted away and was lost to the solar wind. Once the hydrogen is gone, you cannot make water again. Water requires hydrogen. Venus had exhausted the hydrogen budget of its oceans and could not replace it. Now the runaway greenhouse entered its final phase. With the oceans gone, there was nothing left to absorb the CO2 that Venus's volcanoes were continuously belching into the atmosphere. On Earth, volcanic CO2 is scrubbed from the atmosphere by rain, which combines with CO2 to form carbonic acid, which dissolves rock, which locks the carbon into stable mineral deposits on the seafloor. This process, called the carbonate-silicate cycle, is Earth's long-term thermostat. It's what has kept our planet habitable for 4 billion years. Venus lost this thermostat when it lost its water. With no rain, no oceans, and no chemical weathering of any real magnitude, all the CO2 that Venusian volcanoes release just accumulated in the atmosphere, century after century, millennium after millennium, million year after million year. For hundreds of millions of years, Venus vented CO2 into a sky that had no way to remove it. And that is why Venus's atmosphere is 96.5% carbon dioxide today. And that is why the surface pressure is 92 atmospheres. Because for something like 1 billion years, Venus was a volcanic planet with no ocean to hide its exhaust from. Every gram of CO2 that ever escaped a Venusian volcano is still up there, still pressing down, still trapping heat. The greenhouse effect built up to unimaginable levels. On Earth, the greenhouse effect warms our surface by about 33 degrees Celsius. The difference between the minus 18 degrees Celsius average we'd have without an atmosphere and the plus 15 degrees Celsius average we actually enjoy. On Venus, the greenhouse effect warms the surface by about 500 degrees Celsius. Without its atmosphere, Venus would have a surface temperature around minus 40 degrees Celsius. With its atmosphere, it has a surface temperature of plus 464 degrees Celsius. The greenhouse effect on Venus is not a nudge. It is not a factor. It is the dominant fact of the planet's existence. Everything else, the acid clouds, the crushing pressure, the sulfurous chemistry, flows from that one central catastrophe. And here is the part that should keep everyone awake at night. Venus is a warning. Venus is what a runaway greenhouse effect looks like when it goes to completion. It is not a hypothetical scenario. It is not a computer model. It is a real planet orbiting our real sun right now at a real distance we can see with a small telescope from any dark backyard. And it demonstrates, with the full weight of physical evidence, what happens when a rocky planet with an atmosphere loses control of its climate. The mechanism that killed Venus is the same mechanism that operates in Earth's atmosphere today. The same feedback loop involving the same water vapor driven by the same greenhouse gases on a planet that receives less solar energy but is now, thanks to us, accumulating CO2 at a rate that Venus could only have dreamed of. I am not going to belabor the climate change comparison. This is not a lecture about carbon emissions. But I would be dishonest if I told you the story of Venus without acknowledging that Venus is not just a curiosity. Venus is a demonstration. Venus is a data point in the argument about what atmospheres can and cannot survive. Venus is the empirical proof that runaway greenhouse effects are physically possible on Earth-sized planets orbiting sun-like stars, because we can see one, and it is right next door. Now, to be clear, Earth is not going to become Venus, not from anthropogenic CO2 emissions alone. The solar energy Earth receives is not sufficient at current levels to trigger a full runaway. Climate scientists who have modeled this carefully, people like James Hansen and Colin Goldblatt, have found that Earth would need something like a 10-fold increase in solar energy input, or an atmospheric CO2 concentration well above 30,000 parts per million. We're currently at about 425 parts per million. to enter a true runaway state comparable to what Venus experienced. But we do not need to become Venus to become badly damaged. Long before a full runaway, we would see civilization-ending disruptions from what are, in the geological sense, quite modest climate changes. A few degrees of warming is enough to reshape agriculture, flood coastlines, and displace hundreds of millions of people. A few more degrees on top of that begins to threaten the habitability of large portions of the tropics for outdoor human activity. Venus, in this sense, is not the near-term threat. Venus is the outer edge of the possibility space. Venus is what tells us the possibility space includes things worse than we can easily imagine. And Venus is a scientific gift in a strange, dark way, because Venus is a laboratory. Venus lets us study with actual physical measurements what a runaway greenhouse looks like when it has already happened. Every probe we send to Venus is not just exploring another world, it is examining a cautionary tale. It is investigating a case study in atmospheric death. I want to take a break from the horror for a moment and talk about how Venus is shaped, because Venus's geology is one of the most bizarre and unresolved topics in planetary science, and it deserves attention on its own terms. The Magellan radar mapping of the early 1990s revealed a Venus that was, in some ways, familiar and in other ways deeply strange. There are volcanoes, thousands of them, more per unit area than on any other rocky body in the solar system. There are mountains, some of them very tall. There are impact craters, though far fewer than you might expect. There are vast plains of solidified lava. There are things that don't quite fit any Earth analog. Let me start with what's missing, because absence tells us something. Venus has almost no small impact craters. On the Moon, on Mars, on Mercury, every rocky, airless, or thin atmosphered surface, you find craters of every size, from meters to hundreds of kilometers. Venus's atmosphere is so thick that small meteoroids burn up before reaching the surface. Anything smaller than about a kilometer across is destroyed on entry, either fragmenting into smaller pieces that air brake to harmless velocities or vaporizing entirely. So Venus is missing its small craters. That's expected. What is not expected is that Venus's large craters, the ones that do exist, are almost uniformly distributed across the planet's surface, and they are almost uniformly of similar age. This is deeply weird. On Earth, we have craters of many ages, from ones that are billions of years old to ones that formed last century. On Mars, the same. On the Moon, the same. Every planet with a preserved surface shows a mix of crater ages, because impacts have been happening continuously throughout the solar system's history, and some regions of every planet are older than others, and older regions have more craters than younger regions. Venus does not work this way. Venus's craters, there are about 1,000 of them, large enough to be visible to Magellan's radar, appear to all be roughly the same age. They are distributed roughly evenly across the entire planet. There are no ancient heavily cratered regions and no crater-free young regions. There is just an even scattering of similarly aged craters everywhere. This is not what a normal planet looks like. This is what a planet looks like if, at some point in its recent geological past, the entire surface was replaced at once. The mainstream interpretation of this observation, developed in the 1990s and still the leading hypothesis today, is that Venus experiences catastrophic global resurfacing events. Somewhere between 300 and 700 million years ago, the number is fuzzy, and the resurfacing may not have been simultaneous everywhere. Nearly all of Venus's surface was covered by fresh lava flows. Every crater that existed before this event was buried. Every mountain range, every plain, every feature was overwritten by a global outpouring of magma from Venus's interior. Since then, the planet has been mostly quiet, geologically speaking, and the craters we see today are the ones that have accumulated in the roughly 500 million years since the resurfacing. If this hypothesis is correct, and it remains contested, there are alternative models involving more gradual, continuous resurfacing. Then Venus is a planet that periodically destroys itself every few 100 million years, or every billion years, or on some irregular schedule. The interior heat that has been building up beneath the crust breaks loose and repaves the entire world. This does not happen on Earth. On Earth, we have plate tectonics, a system of moving crustal plates that continuously recycles surface material through subduction zones, allowing the planet's interior to shed heat gradually and continuously. Earth's crust is renewed constantly, but never all at once. Different regions have different ages, and the process is smooth. Venus does not appear to have plate tectonics. There are no obvious subduction zones. There are no mid-ocean ridges. The crust seems to be one continuous immobile shell sitting on top of a hot interior with no efficient way to release its heat. So the heat builds up and builds up. And then, on some timescale, in some manner that we don't fully understand, the crust fails all at once, and the interior heat vents catastrophically through global volcanism, and the planet remakes itself, and then it goes quiet again for another 500 million years. This is one hypothesis anyway. It might be wrong, but if it's right, it means Venus is not just a hot planet. Venus is a planet that periodically explodes, a planet whose surface is destroyed and rebuilt on schedule, a planet where geological time works in violent lurches rather than smooth flows. Now let me tell you about the specific features that don't fit anywhere else in the solar system. Corona coronae, plural of corona, meaning crown, are large, roughly circular geological features found only on Venus. They range from about 60 kilometers to over 2,000 kilometers in diameter. They are bounded by rings of ridges and troughs, and their interiors often show volcanic and tectonic deformation. The current best explanation is that corona form when a plume of hot material rises from Venus's deep interior, pushes up the crust from below, causes localized volcanism, and then, as the plume cools, the whole region subsides, leaving a ring-shaped scar. This mechanism has no exact Earth analog. On Earth, hot mantle plumes create things like the Hawaiian island chain or the Yellowstone hotspot. But they don't create these roughly circular ring-bounded features because Earth's crust is moving and the plumes get smeared into linear tracks. Venus has hundreds of coronae. They are one of the defining features of Venusian geology, and they are found nowhere else in the solar system. Recent research, including a 2020 study by scientists at the University of Maryland and the ETH Zurich, has suggested that at least 37 coronae on Venus show signs of active geological processes. The plumes may still be rising. The ground may still be deforming. Venus in these regions may not be a dead world, but a slowly breathing one. Tesserae are among the strangest terrains on Venus. The name comes from the Greek word for tiles, because these regions are broken into complex intersecting patterns of ridges and grooves that look from orbit like a mosaic of tiles that have been stacked and shifted against each other. Tesserae are the oldest known surfaces on Venus. They stand higher than the surrounding plains, and they appear to have been deformed by multiple episodes of tectonic activity before the global resurfacing event. When the lava flooded across Venus, tesserae remained as islands of older, higher ground, surrounded by seas of fresh basalt. We do not fully understand how tesserae form. They may be the remnants of ancient continental crust, the kind of lighter, silica-rich crust that forms on Earth through prolonged interaction with water. If so, they would be evidence of Venus's early oceans, preserved as elevated ruins after the water was gone. This is why tesserae are among the top priority landing sites for future Venus missions. If we could put a lander on a tessera and analyze its composition, we might be able to determine whether it formed in the presence of water. And if it did, we would have direct evidence that Venus was once a wet world. Volcanoes and pancake domes. Venus has more volcanoes than any other body in the solar system. Magellan's radar identified over 1,600 major volcanoes and volcanic features, and estimates of smaller volcanic centers run into the hundreds of thousands. Most of these volcanoes appear to be dormant, in the sense that we don't see obvious signs of current eruptions. But dormant and extinct are not the same thing, and evidence has been accumulating for years that Venus is, in fact, still volcanically active. In 2023, planetary scientist Robert Herrick and his collaborators working with reprocessed Magellan data identified what appears to be an active volcanic vent on the northern flank of Mont Mons, one of Venus's largest volcanoes. Comparing radar images taken 8 months apart in 1991, they found that the shape of the vent had changed, expanded and deformed in ways consistent with an active eruption. This was the first direct evidence of ongoing volcanic activity on Venus, and it strongly suggests that Venus is not a dead planet, but a currently erupting one. We just haven't been watching it closely enough for long enough to catch the eruptions in progress. Meanwhile, Venus has a type of volcanic feature that is essentially unique to itself: the pancake dome. These are broad, flat-topped, roughly circular volcanic structures, typically 20 to 50 kilometers across, with steep sides and remarkably flat tops. They look from orbit like enormous pancakes that have been dropped onto the surface from above. Pancake domes appear to form from very viscous lava, silica-rich, thick, slow-flowing magma that piles up rather than spreading out. On Earth, we get similar features from rhyolitic lava, but never at the scale of Venus's pancake domes, because Earth's gravity and atmosphere and crustal recycling don't allow them to grow so large. Venus's pancakes are geological monsters, 40 times larger than their Earth cousins, sitting on the surface of a planet that has nothing else to disturb them. Maxwell Montes and Ishtar Terra. I've mentioned Maxwell Montes briefly. It is Venus's highest mountain, rising 11 kilometers above the mean planetary radius. It is part of a highland region called Ishtar Terra, which is roughly the size of Australia in Venus's northern hemisphere. Ishtar Terra and its southern hemisphere counterpart, Aphrodite Terra, are the two great highland regions of Venus, roughly analogous in scale to Earth's continents, though not in origin. They rise above the surrounding lowland plains, and they contain most of Venus's tessera terrain, most of its tallest mountains, and most of its oldest surface features. Maxwell Montes itself, at the eastern end of Ishtar Terra, is a spectacular feature. It's higher than Everest, it's steep, it's coated, as I mentioned earlier, in metallic frost, and it's named, this is a small piece of trivia, after James Clerk Maxwell, the Scottish physicist whose equations describe electromagnetism, because Venus was mapped by radar, which uses electromagnetic waves, and the naming convention wanted to honor the theoretical foundation of the mapping technology. Maxwell Montes is the only major feature on Venus named after a man. Every other named feature, every corona, every mountain, every plain, every crater, is named after a woman, real or mythological. This is the International Astronomical Union's convention. Because Venus is named after a goddess, its features are named for women. Matmons is named for the Egyptian goddess of truth. Ishtar Terra is named for the Babylonian goddess of love and war. Aphrodite Terra is named for the Greek goddess of love. Sacagawea Patra is named for the Shoshone woman who guided Lewis and Clark. Cleopatra Crater is named for the Egyptian queen. The list goes on for thousands of features. Venus is, cartographically, the most female place in the solar system. There is something appropriate about this, that the most hostile world we know is also the one we have named entirely for women, drawing on a global mythology of goddesses both nurturing and destroying. Venus, the planet, embodies both aspects of its namesake. It is beautiful in the sky. It is deadly on the ground. It is named for love, and it will melt you. The possibility of life. I promised I would return to this, and now I will. The question of whether Venus is or has been inhabited is one of the most fascinating, contentious, and consequential questions in astrobiology. Let me lay out what we know, what we don't know, and why the question refuses to die despite the seeming absurdity of asking it. Ancient Venus. Let's start with the past. Was ancient Venus habitable? The evidence increasingly says yes. Climate models developed at NASA's Goddard Institute for Space Studies, most notably by Michael Way and his colleagues, have shown that Venus could have maintained liquid water oceans and temperate surface conditions for as long as 3 billion years. 3 billion years is a long time. For context, life on Earth arose within the first billion years of our planet's existence, and complex life took another 2 to 3 billion years to develop. If Venus had 3 billion years of habitable conditions, that is more than enough time, in principle, for life to have arisen there. Not just microbial life, potentially complex life if the same evolutionary pressures operated there as here. But we don't know if life arose. We have no direct evidence. The evidence for ancient habitability is entirely theoretical. Climate models, mineralogical inferences, comparisons to Earth's early history. Nothing we have directly measured on Venus proves that oceans existed there. The tesserae might be continental remnants, but we haven't landed on one and analyzed its composition. The composition of Venus's atmosphere is consistent with a wet past, but it's also consistent with alternative histories that don't require large oceans. If life did arise on ancient Venus, it faced extinction when the runaway greenhouse triggered. Surface life would have died as the oceans evaporated and the temperature climbed. Subsurface life might have persisted longer in deep aquifers or hydrothermal systems, but eventually, as the planet's water was lost to space, even subsurface life would have run out of its essential solvent. Any life that developed on ancient Venus is almost certainly extinct by now. Almost certainly. Almost. The clouds here is where things get strange. Here is where I have to tell you about phosphine. In September 2020, a team of astronomers led by Jane Greaves of Cardiff University announced the detection of phosphine gas. Chemical formula PH3, a compound of phosphorus and hydrogen, in Venus's cloud layer. The detection was made using two different ground-based radio telescopes, the James Clerk Maxwell Telescope in Hawaii and the ALMA Array in Chile, observing at millimeter wavelengths and finding an absorption feature at the specific frequency where phosphine molecules resonate. The concentration was small, about 20 parts per billion, but it should have been zero. Phosphine is what chemists call a reduced compound. It contains phosphorus in its lowest oxidation state, bonded to hydrogen. It is chemically incompatible with oxidizing environments like Venus's atmosphere, which is full of sulfuric acid and carbon dioxide and should destroy phosphine molecules on contact. Any phosphine in Venus's clouds should be broken down within minutes to hours. For phosphine to be present at detectable concentrations, something must be continuously producing it, fast, in large amounts, all the time. On Earth, phosphine is produced by two known mechanisms. The first is industrial. We manufacture it for use in semiconductor fabrication and as a fumigant. The second is biological. Certain anaerobic microorganisms produce phosphine as a metabolic byproduct, particularly in environments like swamps, wetlands, and the intestinal tracts of animals. That's it. Those are the only two known sources of phosphine on Earth. There is no known abiotic, non-biological, non-industrial process that produces phosphine at anywhere close to the concentrations observed on Venus. The Greaves team went through every possibility they could think of. Lightning, not enough. Volcanic outgassing, not the right chemistry. Photochemistry in the upper atmosphere, wrong energy levels. Delivery by meteorites or comets, insufficient rate. They couldn't explain the phosphine through any known abiotic process. So they published cautiously the possibility that life might be involved, not as a claim, but as a hypothesis that could not be ruled out, and the scientific community erupted. The immediate response was a wave of criticism, some of it valid, some of it reflexive. Various researchers questioned the data analysis, arguing that the phosphine signal might be an artifact of processing artifacts or confusion with other atmospheric compounds like sulfur dioxide. Others accepted the detection, but proposed alternative abiotic sources, some form of unusual atmospheric chemistry perhaps, or a slow leak from Venus's interior. The debate is still ongoing as of 2026. The original Greaves detection has been re-examined multiple times, sometimes confirmed, sometimes not. Follow-up observations by other telescopes have found phosphine sometimes, and sometimes not, at concentrations that vary from below the detection limit to consistent with the original claim. It's messy, it's confusing, it's unresolved. But here is what has become increasingly clear over the past few years. Something strange is happening in Venus's atmosphere, whether it's phosphine specifically, or some other biosignature molecule, or just an unusual chemistry that we don't yet understand. Venus's clouds are chemically weirder than we can currently explain. In addition to phosphine, there have been reported detections of ammonia, another compound that shouldn't survive in Venus's oxidizing environment. And of course, the ultraviolet absorbers that have been unidentified for a century. Here is the honest scientific position as of 2026. We do not know whether life exists in Venus's clouds. We cannot rule it out. The chemistry of the clouds includes features that are difficult to explain without invoking either biology or some novel abiotic process that we haven't discovered yet. Either explanation would be scientifically significant. Both explanations remain live possibilities. What life on Venus would have to be. Let's think briefly about what Venusian cloud life would have to look like if it exists. It would have to survive in concentrated sulfuric acid. This is not impossible, but it is hard. Life would need some kind of protective envelope, either a cell wall made of acid-resistant materials or an internal chemistry that runs on sulfuric acid rather than water. On Earth, life uses water as its universal solvent. Venusian cloud life would either need to use water within an acid-resistant capsule, or it would need to use sulfuric acid itself as its solvent, which would require a completely different biochemistry from anything we know. It would have to survive without a solid substrate. Earth's microorganisms usually live on surfaces, soil grains, rock faces, the interiors of other organisms. Venusian cloud microbes would live in droplets, suspended in the air, drifting with the winds. There is no ground for them to attach to. Their entire life cycle would happen within the cloud layer. It would have to reproduce fast enough to compensate for droplets falling out of the cloud layer. Sulfuric acid droplets in Venus's atmosphere don't stay at their altitude forever. They condense, grow, fall into the lower atmosphere, evaporate as they encounter hotter air, and rise again as vapor. Any organism living in the droplets has to complete its life cycle, including reproduction, before its home droplet falls into the sterilizing heat below. This has been dubbed the airborne life cycle problem for Venus, and it's one of the strongest theoretical arguments against long-term cloud biospheres. Sarah Seeger, an MIT astrophysicist who has thought carefully about this, has proposed a possible solution: that Venusian microbes might have a dormant spore phase that lets them survive being cycled down into the lower atmosphere, riding out the heat in some inert form, and then rising again with the convective updrafts to be resuspended in the cloud layer where they can wake up and reproduce. It's speculative. It's not impossible. It requires an organism significantly more robust than anything we know on Earth. But it's a coherent hypothesis, and it can't be ruled out without more data. The organism would also have to source its energy from something. Sunlight is available in the cloud layer. The clouds are, after all, absorbing sunlight. That's part of why Venus is so hot. Chemical energy is available too, in the form of the various sulfur compounds that permeate the atmosphere. There's no shortage of potential metabolic pathways. The question is whether any organism, having evolved from whatever ancestor, could actually use them. If Venusian cloud life exists, it is not related to Earth life. There is no plausible mechanism by which Earth microbes could have crossed to Venus and adapted to sulfuric acid clouds. Any Venusian life would represent a completely independent origin, a second genesis of life in the same solar system using different chemistry from ours. If we find that, if we prove it, if we bring back a sample and analyze its molecular structure and find that it is fundamentally alien in its construction, different amino acids, different nucleic acids, different fundamental molecular chirality, then we will have answered one of the great questions of science. Life in the universe will not be a fluke, one-time event on Earth. It will be a common outcome of planetary chemistry arising independently on multiple worlds, even within a single star system. The implications of that are staggering. If life arose twice in one solar system, it has almost certainly arisen countless times across the galaxy. The universe, in that case, is teeming with life, and we have simply been too far away and too poorly equipped to see it. Or, and this is the other possibility, the phosphine is an artifact. The ammonia is a misidentification. The UV absorbers are some exotic chemistry we haven't yet worked out. And Venus's clouds are lifeless, and Venus is a dead planet through and through, and we are alone in this solar system. We don't know. And that's why the next generation of Venus missions matters so much. 40 years of silence on the Venusian surface is about to end. There are, as of 2026, several Venus missions in active development, funded, and progressing toward launch. This is the largest wave of Venus exploration since the 1980s, and it is being driven, in significant part, by the phosphine controversy and the renewed interest in Venus as a potential astrobiology target. Let me walk through the major ones. Da Vinci, NASA Da Vinci, which stands for Deep Atmosphere Venus. Investigation of noble gases, chemistry, and imaging is a NASA mission scheduled for launch in 2029, with arrival at Venus in the early 2030s. It consists of two parts, a flyby carrier spacecraft and a descent probe. The descent probe is the exciting part. It is designed to fall through Venus's atmosphere for about an hour, taking measurements the entire way down. It will sample the atmospheric chemistry at multiple altitudes with unprecedented precision. It will measure noble gas concentrations, which will help constrain the history of Venus's atmosphere. It will search for organic compounds. It will image the surface as it approaches, providing the first close-up photographs of a Venusian tessera region. Da Vinci is not designed to survive landing. It is a descent probe, not a lander. If it happens to survive impact, it will transmit for as long as it can, potentially minutes to tens of minutes, but its main mission is the descent itself. This is deliberate. Landing on Venus is hard. Descending through Venus's atmosphere while transmitting data is somewhat easier, and it captures most of the scientific value. Da Vinci's primary target is a tessera region called Alpha Regio, one of the ancient highland areas that might preserve chemical signatures of Venus's wet past. If Da Vinci can measure the composition of a tessera surface, even briefly, we might finally answer whether Venus had oceans. Veritas, NASA Veritas, standing for Venus Emissivity, Radio Science, INSAR, Topography, and Spectroscopy, is a NASA orbiter mission that will produce the highest resolution radar maps of Venus ever obtained. It will improve on Magellan's mapping by roughly a factor of 10 in resolution and will detect surface changes over time, allowing us to identify active volcanism directly by comparing images taken months or years apart. Veritas was originally scheduled for launch in 2028, but its development timeline has been repeatedly delayed due to funding and technical issues at NASA. As of early 2026, its status is uncertain, but the mission is still officially part of NASA's planetary science portfolio and is expected to launch in the early 2030s. Vision, European Space Agency. Envision is an ESA orbiter mission scheduled for launch in 2031. Like Veritas, it will map Venus at high resolution, but with different instrumentation emphasizing subsurface radar sounding and detailed atmospheric spectroscopy. Envision will look for evidence of active volcanism, seismic activity, and current geological processes. It will attempt to characterize the composition of surface materials and understand how the surface and atmosphere interact. Together, Veritas and Envision represent the modern replacement for Magellan, a pair of orbiters that will give us our first truly detailed global view of Venus in over 3 decades. Shukrayan-1, India. The Indian Space Research Organization is developing Shukrayan-1, a Venus orbiter mission that has been in planning since the mid-2000s. Its current planned launch is in 2028, though schedules have slipped repeatedly. It will carry a suite of instruments to study the atmosphere, ionosphere, and surface. Notably, it may include a balloon or atmospheric probe as a secondary payload, which would give India its first direct atmospheric exploration of another planet. Venera D, Russia, long delayed. Russia has been discussing a return to Venus for over 2 decades under the name Venera D. The mission concept includes both an orbiter and a lander, with the lander designed to survive on the surface for a much longer period than any previous Venusian lander, potentially days, using advanced high-temperature electronics. Venera D has never launched, and its future is unclear given Russia's current geopolitical and economic situation. It remains a possibility rather than a scheduled reality. The Rocket Lab mission. And then there is one small, strange, private effort that I want to highlight because it is the kind of thing that could only exist in our current era of space exploration. Rocket Lab, the American-New Zealander commercial space company best known for its Electron rocket, has been developing a small Venus atmospheric probe on its own initiative. The mission is being led by Peter Beck, Rocket Lab's CEO, in collaboration with MIT researchers including Sarah Seeger. The plan is to send a small probe, roughly 1 meter across, weighing less than 20 kilograms, into Venus's atmosphere, where it will spend about 5 minutes falling through the cloud layer, sampling the chemistry with a single dedicated instrument optimized to detect organic molecules. 5 minutes, that's all. A cheap, small, focused mission with one primary goal: to determine whether there are organic compounds in Venus's clouds that could indicate the presence of life. The mission has faced multiple delays, and as of early 2026 is still awaiting launch. But if it flies, it will be one of the first privately funded interplanetary missions in the history of spaceflight, and it will attempt to answer one of the biggest questions in science with a spacecraft the size of a microwave oven. There is something poetic about this, that after 50 years of massive government-funded probes being crushed by Venus one after another, the next attempt might come from a startup using a small commercial rocket with a single instrument aimed at a single question. It is a very 21st century way to explore the solar system. The long-term vision. Habitable cloud cities. I want to end this section with something speculative but not entirely fictional. In 2015, NASA researchers published a concept study called HAVOC, High Altitude Venus Operational Concept. The study explored the feasibility of sending crewed aircraft and eventually habitats into Venus's upper atmosphere. Because at 50 to 55 kilometers altitude, Venus's atmospheric pressure is 1 Earth atmosphere, and the temperature is 30 to 70 degrees Celsius, and Venus's gravity is 90% of Earth's. These are conditions in which humans can survive with minimal life support, protected only from the sulfuric acid and provided with breathing air. The HAVOC concept envisioned enormous helium or hydrogen-filled airships drifting at 50 kilometers altitude, containing crews of astronauts who could work and live for weeks or months at a time. Because Earth's normal air, a mixture of nitrogen and oxygen, is less dense than Venus's carbon dioxide atmosphere, a habitat filled with ordinary breathable air would actually float in Venus's atmosphere the way a helium balloon floats in Earth's. You wouldn't need special lifting gas. The habitat itself, filled with breathable atmosphere, would be a lifting body. Picture that for a moment. A city in the sky of Venus. A vast floating structure kilometers across, filled with ordinary air, drifting eternally through the acid clouds, while inside its walls, people live at normal Earth pressure and Earth-like temperatures, growing food in hydroponic bays, walking through corridors, looking out through acid-resistant windows at the orange sky and the endless cloud tops. There would be dangers, of course. The acid outside would corrode any exposed surface. The winds would move the habitat continuously around the planet. A full circumnavigation every 4 days, driven by Venus's super-rotating atmosphere. Escape to orbit would be difficult. You would need a rocket capable of reaching Venusian orbital velocity, launch from a moving airship platform 50 kilometers above the surface. Return to Earth would be a challenge on top of the challenge, but the physics allows it. The engineering, while difficult, is not fundamentally impossible. And in some far future, 100 years from now, or 200, or 5, Venus might be a place where humans go and stay in the clouds. Some researchers have gone further and suggested that Venus's cloud layer might be, in some ways, easier to colonize than Mars's surface. Mars offers a solid surface, which is nice, but it also offers 1% of Earth's atmospheric pressure, killing radiation, cold that requires constant heating, and a soil full of perchlorates. Venus's clouds offer breathable pressure air, temperatures that require minimal heating or cooling, near Earth normal gravity, and significant protection from cosmic radiation by the atmosphere above the habitat altitude. Venus is a hell world at its surface. But 50 kilometers up, Venus is the most Earth-like environment in the solar system besides Earth itself. This is a very strange fact, and it is one of the reasons that Venus, despite its horror, has not been entirely written off as a target for future human presence. Not soon. Not in our lifetimes, probably. But eventually, perhaps. I want to end this by returning to something I mentioned near the beginning and giving it the weight it deserves. Venus is a mirror. That is the phrase I keep coming back to, and I want to explain what I mean by it more carefully now that we have all the pieces on the table. Venus is a mirror because it shows us what Earth could have been, and what Earth might still become, and what the universe contains in the way of planetary fates. When you look at Venus, you are not looking at an alien world in the deep sense. You are not looking at Jupiter with its incomprehensible mass and its metallic hydrogen and its storms the size of continents. You are not looking at Titan with its methane lakes and its cryogenic chemistry. You are not looking at Pluto or Enceladus or any of the other exotic places in the outer solar system that operate on physics utterly foreign to our experience. You are looking at a planet the same size as Earth, the same mass, the same density, the same starting composition, the same basic geological materials, silicate rocks and metallic core and volcanic crust, a planet that received the same rain of comets and meteorites in the early solar system that condensed from the same protoplanetary disk that started out mock by every available line of evidence as an essentially identical twin to Earth. And now it is a nightmare. Something happened to Venus that did not happen to Earth. The difference between the two planets today is enormous. One is a paradise of oceans and forests and cities and life. The other is a crushed, cooked, acid-soaked hell. But the difference between the two planets at their origins was small. Small enough that if you had visited the young solar system 4 billion years ago, you might not have been able to tell which one would go on to host life and which one would go on to melt lead. The small difference was location. Venus formed 30% closer to the sun than Earth. That's it. That was the initial condition that drove the divergence. Everything else that distinguishes the two planets today, the missing oceans, the toxic atmosphere, the ferocious heat, the crushing pressure, the acid clouds, the dead surface, all of that emerged over billions of years from that one small difference in solar distance, amplified by feedback loops, cascaded through geochemistry, until the two twins that started so similar ended up almost as different as it is possible for two rocky planets to be. This is what a mirror does. It shows you a version of yourself that is you, but not you. That has your face, but not your life. That is what you might have been under slightly different circumstances. Venus tells us that planets are contingent, that the specific conditions of a specific world at a specific moment matter and can determine the entire subsequent history of that world across billions of years. Venus tells us that habitability is fragile, that the difference between a living world and a dead one can be smaller than we intuitively believe, that runaway processes are possible, that once a planet starts to tip in a certain direction, there may be no path back. Venus also tells us that dead worlds can look, from far away, remarkably beautiful. Venus is the brightest object in the night sky besides the moon. Venus is what ancient civilizations called the morning star and the evening star. Venus is a jewel to the naked eye, a diamond in the twilight, a promise of something bright and beautiful and near. But if you go there, if you actually go to the place that shines so pleasantly at dusk, you find that the shine is nothing more than reflected sunlight bouncing off acid clouds. And beneath the acid clouds is death. There is a lesson in this, if you want one, about how the surface appearance of a thing can be very different from its inner nature, about how the light we see from a distant object tells us less than we think, about how prettiness can conceal horror and often does. I've tried in the 20,000 words or so of this conversation to give you Venus as it actually is, not as it appears in the sky, not as a romantic symbol, not as a poetic name attached to a bright dot, but as a physical place, a real, actual, existing world with a surface and a sky and a chemistry and a history. A place that would kill any living thing in seconds if that living thing were placed on its ground. A place that has swallowed dozens of our best machines and left them as scattered corpses across its plains. A place that spins backward and slowly, that has a day longer than its year, that reflects our sunlight back at us with such perfect deceptive brilliance that ancient humans mistook it for two different stars because they could not believe one object could shine so consistently. I have tried to give you Venus honestly, its beauty and its horror both, its scientific mysteries and its philosophical implications, its history of exploration and its future of continuing questions, its role as our sister world and its role as our warning. Venus is a real place. It is 41 million kilometers away as I write this. It is rotating slowly on its axis, backward, over the course of 243 Earth days. It is being lashed by 400 km/h winds in its cloud tops. Its surface is glowing dull red from stored infrared heat. Its lightning is strobing in its clouds. Its volcanoes are, in at least some places, still erupting. Its atmosphere is doing chemistry that we do not fully understand. Its history is written in features we have not yet visited. Its future is unknown. And if you go outside tonight at dusk or before dawn and look at the western or eastern sky, you may see it, a single brilliant point of light, brighter than any star, steady where the stars twinkle, patient in the sky where all our attention passes and returns. It will be beautiful. It will look like a friendly thing. It will look like a companion. It is not a companion. It is a graveyard. It is our sister who died. It is the world that shows us, more clearly than any theoretical model or computer simulation, what can happen to a planet that starts out well and ends up otherwise. Look at it anyway. It is worth looking at. It is worth thinking about. It is worth understanding in as much depth and detail as we can manage, because Venus is one of the two closest examples we have of what a rocky planet can be, and the other example is the one we live on, and the difference between the two is not as large as we would like it to be. Venus is our sibling. Venus is our warning. Venus is beautiful in the sky and terrible on the ground. And Venus, for all its horror, is not finished with us yet. There are missions coming. There are questions still to be answered. There is life, perhaps, in its clouds, or there is not, and we need to find out which. There's a story still being written about our understanding of what Venus is and what Venus means. I have described Venus's environment in abstract terms: temperatures, pressures, chemistries. Now I want to be specific and physical. I want to describe as precisely as I can what would happen to a human being who was placed, unprotected, on the surface of Venus. This is not a pleasant exercise, but it is worth doing because it makes the numbers real. When I tell you that Venus's surface is 464 degrees Celsius, that fact only means something when you translate it into what those temperatures actually do to organic matter. When I tell you the pressure is 92 atmospheres, that fact only becomes visceral when you understand what 92 atmospheres does to human tissue. Venus's hostility is often described in numbers because numbers are precise, but the numbers hide the horror. Let me unhide it. The first second. Imagine, for the sake of the thought experiment, that a human being is teleported instantaneously from Earth's surface to Venus's surface. They arrive intact, alive, and conscious, standing on Venusian ground in ordinary clothes with no protective equipment. What happens in the first second? Several things happen simultaneously, and they interfere with each other in ways that make it hard to describe them in order. But let me try. The first thing is the pressure. The pressure at Venus's surface is 92 times Earth's atmospheric pressure, equivalent to being submerged 900 meters underwater in Earth's oceans. Human bodies are largely incompressible because we are mostly water, and water does not compress much even under extreme pressure. So the immediate effect on the body's tissues is less dramatic than you might expect. Your bones don't crumble. Your muscles don't collapse. You do not implode. But your lungs are not water. Your lungs are gas-filled. And gas does compress. When the external pressure suddenly rises to 92 atmospheres, the air in your lungs is compressed to 1/92nd of its original volume, essentially instantaneously. Your lung tissue, which is designed to hold air at 1 atmosphere of pressure, cannot handle this. Your lungs collapse. The alveoli, the tiny air sacs where gas exchange happens, are crushed. Any air remaining in your airways is forced deep into your tissues, where it dissolves into your blood at pressures that would be lethal, even if everything else about Venus were survivable. Your sinuses collapse. Your inner ears rupture as the pressure differential between your middle ear and the external environment overwhelms your Eustachian tube's ability to equalize. If your mouth is open, the sudden pressurization forces the Venusian atmosphere down your throat and into your stomach and lungs, filling them with hot carbon dioxide. Simultaneously, and this is happening in the same first second, the temperature is doing its work. 464 degrees Celsius is hot enough to melt lead, zinc, and tin. It is hot enough to cause paper to burst spontaneously into flames without any ignition source. Paper's auto-ignition temperature is 233 degrees Celsius. It is hot enough to melt many kinds of glass. It is roughly the temperature of the inside of a self-cleaning oven at its maximum setting, which is designed to reduce baked-on food residue to ash. The human body is largely water. Water at Venus's surface pressure has a boiling point of about 300 degrees Celsius, well below the ambient temperature. So the water in your body wants to boil, but it can't boil normally because it is contained within tissues that are pressurized to 92 atmospheres. Instead, the water in your tissues undergoes a strange and rapid process of superheating, where it remains liquid despite being far above its normal boiling point, held liquid only by the pressure of the surrounding atmosphere and the constraint of the tissue matrix. Your skin begins to cook immediately. The outer layer, the epidermis, is the first to go. At 464 degrees Celsius, human skin behaves the way meat behaves when dropped into a very hot skillet. It sears, it browns, it releases moisture as steam, and then it chars. Within a fraction of a second, the exposed surfaces of your body, face, hands, any skin not covered by clothing, are undergoing what forensic pathologists would recognize as fourth-degree thermal injury, which is the medical term for burns that penetrate through the skin into underlying muscle and bone. Your clothing, if you are wearing any, ignites. Cotton, wool, polyester, all of it has auto-ignition temperatures well below 464 degrees Celsius. The clothing begins to burn, though the burning is strange because Venus's atmosphere contains almost no oxygen. Normal combustion, the kind that produces bright flames, requires oxygen. On Venus, your clothing would char rather than flame, blackening and disintegrating from the heat alone in an atmosphere that is essentially inert from a combustion standpoint. Your eyes are gone in the first second. The corneas cook, becoming opaque within milliseconds. The vitreous humor, the jelly-like substance filling the eye, boils and expands, rupturing the eyeball. Your vision ends before you have time to register what you are seeing. By the second second, if any of your nervous system is still functioning, and this is doubtful because the brain is a delicate organ that stops working reliably above about 42 degrees Celsius, and your brain is being heated toward Venus's ambient temperature at an extraordinary rate, you would experience something that can barely be described because it has no analog in human experience. Your lungs are already crushed and useless, so you cannot breathe. Even if you could breathe, you would not want to, because inhaling Venus's atmosphere means inhaling supercritical carbon dioxide at 464 degrees Celsius, which would flash cook your remaining airway tissue instantly. But you would not experience suffocation in the normal sense because suffocation takes minutes, and you will not have minutes. Your blood is heating up. The temperature of your circulatory system is climbing at a rate governed by the thermal conductivity of your tissues and the enormous temperature differential between your 37 degrees Celsius body and the 464 degrees Celsius environment. Within a couple of seconds, your core temperature is climbing through 60 degrees Celsius, 80 degrees Celsius, 100 degrees Celsius. At 100 degrees Celsius, at normal pressure, blood would boil. At 92 atmospheres, blood remains liquid, but its proteins, the hemoglobin, the albumin, the enzymes that keep you alive, begin to denature. They unfold. They lose their function. Your blood becomes chemically incapable of transporting oxygen or removing waste. Though this is academic, because your circulation has already stopped, because your heart's muscle proteins are denaturing at the same time. Your sulfuric acid exposure is happening now too, though on Venus's surface there is no liquid sulfuric acid. It exists only in the clouds far above. But the surface atmosphere contains sulfuric acid vapor, and it contains other reactive sulfur compounds: sulfur dioxide, carbonyl sulfide, hydrogen sulfide. That would be reacting with your body's exposed tissues, adding chemical injury to the thermal injury already destroying you. The third second and beyond. By the third second, you are dead. There's no ambiguity about this. Every organ system that could sustain life has been destroyed by the combined effects of heat, pressure, and chemistry. Your brain has cooked. Your heart has stopped. Your lungs are ruined. Your skin is charring. There is nothing left of you that could be revived by any medical intervention, but you continue to be processed by the environment. Over the next minutes and hours, your body would undergo a slow cooking that has no equivalent on Earth. Your outer tissues would char completely, becoming a blackened crust. Your inner tissues, protected somewhat by the outer layers, would cook more slowly, achieving something like the consistency of pot roast that has been left in the oven for far too long. A dense, dry, protein-denatured mass with the water largely driven out. The sulfur compounds in the atmosphere would continue to react with your remains, particularly with any exposed metal: the iron in your hemoglobin, the calcium in your bones, the trace metals in your tissues. Iron sulfide would form on exposed surfaces. Your bones, over time, would begin to react with the atmospheric chemistry in ways that no forensic analysis has ever had to consider, because no forensic analysis has ever been performed on a body left on Venus. Eventually, over weeks, months, years, what remained of you would slowly break down into something unrecognizable. Not through decomposition in the biological sense, because there are no microorganisms on Venus's surface, as far as we know, to decompose you, but through pure chemistry. The heat and the reactive atmosphere would slowly convert your carbon into carbon compounds that fit the local equilibrium. Your carbon would end up in the atmosphere, mostly as CO2. Your calcium would end up in surface minerals. Your iron would end up as sulfides. Your identity, your body, your existence as a discrete organic being would be gradually erased, not decomposed, erased, assimilated into the general chemistry of Venus, which is the chemistry of a planet that does not accommodate anything as complex as life. Compared to other deaths, I want to compare this to other ways a human body can be destroyed in the solar system because context matters. If you were exposed to hard vacuum, say if you were ejected from an airlock without a spacesuit, you would die, but you would die relatively slowly and relatively intact. You would have about 15 seconds of useful consciousness before oxygen deprivation shut down your brain. Your body would not explode. The skin is strong enough to contain the internal pressure. You would experience painful decompression as gases in your tissues expanded. You would freeze slowly over hours because vacuum is a good insulator. Your body would remain recognizable indefinitely, drifting in space, essentially mummified by the cold and the vacuum. A body ejected from the International Space Station could, in principle, be recovered and identified thousands of years later. If you were dropped onto the surface of Mars without protection, you would die from asphyxiation and cold, taking 1 to 2 minutes. Your body would freeze solid within a day and would remain preserved essentially forever, protected from decomposition by the lack of liquid water and microorganisms. If you were dropped into Jupiter's atmosphere, You would die from crushing pressure long before reaching anything resembling a surface, and your remains would be dispersed and dissolved into the immense gaseous body of the planet, becoming indistinguishable from the atmosphere itself. Venus is worse than most of these deaths in the visceral, immediate sense. It combines mechanisms, thermal, mechanical, chemical, that are each individually fatal, applying them all at once with an intensity that no Earth environment approaches. If you have ever wondered which place in the solar system is the worst place a human body could find itself, the answer is Venus. Not the outer planets, not the vacuum of space, not the poles of Mercury. Venus. The only environments that would kill you faster or more thoroughly are things like the interior of the sun or the surface of a neutron star. Places where the physics is so extreme that killing you is not even a coherent description of what happens. On the sun, you would not die of any specific cause. You would simply cease to exist as a coherent object, dissociating into plasma so completely that no molecular structure would remain. Venus, at least, would leave a body, however unrecognizable. The impossibility of rescue. One of the things that makes Venus particularly grim as a hypothetical death is that there is no rescue scenario. On Earth, in almost any environment, there is some conceivable rescue. You can be pulled from water before you drown, hauled from a fire before you burn, warmed after hypothermia. Even in extreme environments, medical intervention often has a window during which survival is possible. On Venus, there is no window. The environment kills so quickly and so completely that no plausible rescue technology could arrive fast enough to save you. Even if a rescue vehicle was hovering directly above you, capable of scooping you up in a heat-shielded, pressure-sealed capsule, it could not reach you fast enough. Your death would be complete within seconds of exposure. This is worth acknowledging because it changes how we think about human exploration of Venus. On Mars, if something goes wrong, there are minutes to hours to fix it. Astronauts have time to reach shelter, to repair equipment, to be rescued. On the Moon, similarly. In Earth orbit, the same. Venus's surface offers none of this. Any protective equipment must be perfect, because there is no margin for failure. A single crack in a pressure suit is not an emergency to be addressed. It is instantaneous death. This is one of the reasons that any serious plan for human presence on Venus focuses on the cloud layer 50 kilometers above the surface rather than the surface itself. The clouds are dangerous, but they are dangerous in ways that human engineering can address. The surface is not. Now that I have described what Venus does to Earth life, let me describe what Venus life might actually look like, if it exists, and what its biology would have to be. This is a speculative section, but it is speculative in a disciplined way. We know a lot about chemistry, about biochemistry, about what molecules can do under various conditions. We can reason about what kind of life might be possible on Venus, even if we cannot yet observe it directly. The cloud zone, where life is possible. Let me be clear at the outset. No life we know of, and probably no life that is chemically possible at all, could exist on Venus's surface. The surface is too hot. At 464 degrees Celsius, all organic chemistry breaks down. The complex molecules that biology requires, proteins, nucleic acids, lipids, simply cannot exist at those temperatures. They come apart. The chemical bonds that hold them together are not strong enough to resist the thermal energy of the environment. Some researchers have speculated about very exotic life based on silicon chemistry or on entirely different chemical systems that might function at high temperatures, but these speculations have very little grounding. We have no examples of high temperature life anywhere in the universe that we know of. Even the most extreme thermophiles on Earth, bacteria that live near deep sea hydrothermal vents, top out around 122 degrees Celsius. Above that temperature, water becomes too aggressive a solvent, DNA becomes too unstable, and proteins denature no matter how they are engineered. So Venus's surface is out. If there is life on Venus, it is not on the ground. The clouds are different. In Venus's cloud layer, at altitudes between 48 and 60 kilometers above the surface, conditions become dramatically more benign. At 55 kilometers up, the temperature is roughly 30 degrees Celsius to 70 degrees Celsius. Warm, but survivable for many Earth organisms. The pressure is close to Earth normal, ranging from about 0.5 to 1.5 atmospheres depending on altitude. Sunlight is available. Water vapor is present, though scarce. But there is one enormous problem. The clouds are made of concentrated sulfuric acid, not diluted sulfuric acid, not weak sulfuric acid. The cloud droplets on Venus are 75% to 96% pure sulfuric acid, a solution more acidic than anything found naturally on Earth's surface, more acidic than car battery acid, more acidic than industrial cleaning chemicals. Sulfuric acid at these concentrations will dissolve human skin in seconds. It will dissolve most organic molecules, proteins, sugars, nucleic acids, almost as quickly. It will destroy virtually every biochemistry we know of on contact. Any life in Venus's clouds must be able to survive in concentrated sulfuric acid. This is the central challenge, and any speculation about Venusian life has to address it. Option 1. Acid-resistant envelopes. The first way that life might survive in Venus's clouds is by wrapping itself in something that sulfuric acid cannot penetrate. On Earth, some microorganisms have evolved cell walls made of unusually resistant materials, thick layers of specialized polymers, mineral coatings, waxy lipid membranes. It is at least conceivable that Venusian microbes might have evolved cell walls that are essentially chemically inert to sulfuric acid. What would such a cell wall be made of? Nothing organic that we know of. Most biological polymers, proteins, polysaccharides, most lipids would be destroyed by concentrated sulfuric acid. But there are some materials that resist sulfuric acid remarkably well. Certain fluoropolymers, like Teflon, certain silicon-based compounds, certain highly cross-linked hydrocarbons, and, interestingly, elemental sulfur itself, which is chemically stable in a sulfuric acid environment. Some researchers have speculated that Venusian microbes might have cell walls made of allotropes of sulfur, or of complex hydrocarbon polymers, or of exotic materials that Earth life has never had reason to develop because Earth life has never had to deal with concentrated sulfuric acid. Inside these acid-resistant walls, the interior of the cell could contain water and normal-ish biochemistry, protected from the outside environment. This is chemically plausible, though it faces enormous challenges. Cell walls have to allow nutrients in and waste out. A wall that is perfectly acid resistant is probably also perfectly impermeable to everything else. Any real Venusian cell wall would have to solve the problem of selective permeability in an environment where any imperfection means death. Option 2. Sulfuric acid biochemistry. The second and more radical possibility is that Venusian life doesn't try to keep the sulfuric acid out at all. Instead, it uses the sulfuric acid as its solvent, the way Earth life uses water. This is a genuinely alien idea, and it deserves careful examination. On Earth, water is not just something that life happens to contain. Water is the medium in which all biological chemistry takes place. Proteins fold in water. DNA exists in water. Cellular reactions happen in aqueous solutions. The properties of water, its polarity, its hydrogen bonding, its temperature range as a liquid, its ability to dissolve a huge range of substances, are not incidental to life. They are foundational to it. Life as we know it is inconceivable without water. But water is not the only possible solvent. Any solvent that can dissolve a wide range of chemicals, that remains liquid over a substantial temperature range, and that participates in the right kinds of chemical reactions, could in principle support some form of biochemistry. Sulfuric acid is such a solvent. Concentrated H2SO4 dissolves a wide range of substances. It participates in a rich chemistry of proton transfers and other reactions. It remains liquid across a broad temperature range, from about 10 degrees Celsius to over 300 degrees Celsius. In some respects, it is actually a better solvent than water for certain kinds of chemistry. If Venusian life uses sulfuric acid as its solvent, then it doesn't need to protect itself from the acid. It needs the acid the way we need water. Its biochemistry would be built around sulfuric acid chemistry rather than aqueous chemistry. Its proteins, analogous molecules serving similar functions, would be constructed from monomers that are stable in sulfuric acid rather than in water. Its genetic material would be some polymer that can preserve information in an acid environment. What would such a biochemistry look like in practice? We don't know in detail, but there are constraints and possibilities. The molecules involved would probably be more oxidized than Earth's biomolecules. They would incorporate more oxygen, more sulfur, fewer hydrogens. They would probably rely on different chemical bonds, carbon-oxygen and carbon-sulfur bonds, rather than the carbon-carbon and carbon-nitrogen bonds that dominate Earth chemistry. They might use metal ions in ways different from Earth life. This is speculative, but it is not fantasy. It is chemistry, worked out from first principles, applied to a specific environment. If life exists in Venus's clouds and uses sulfuric acid as its solvent, then it represents a radically different way of being alive, one that our biochemistry textbooks do not describe because Earth has never needed to develop it. The life cycle problem. Whether Venusian life uses acid-resistant envelopes or sulfuric acid biochemistry, it faces a shared and difficult problem: staying in the habitable zone. Venus's atmosphere is dynamic. Clouds condense and dissipate. Droplets grow and fall. What is at 55 kilometers altitude one day may descend to 40 kilometers the next, where the temperature is 150 degrees Celsius, or to 30 kilometers where it is 300 degrees Celsius. Any organism living in the cloud layer risks being carried down into the lower atmosphere by atmospheric circulation, where it will encounter temperatures that destroy it. Sarah Seeger and her colleagues have proposed a solution: a life cycle that alternates between two forms. In the habitable cloud zone, at 48 to 60 kilometers altitude, microbes exist as metabolically active cells. Droplets containing their full biochemistry, growing, reproducing, doing the work of being alive. But as their cloud droplet grows larger and heavier and begins to descend, the microbe transitions to a dormant spore phase. a hardened, metabolically inactive form that can survive the higher temperatures of the lower atmosphere. The spores fall. They enter the hot lower atmosphere. There, they float, not as droplets, but as small, solid particles, denser than the atmosphere, but not by much, held aloft partially by the atmospheric density and partially by convective updrafts. Eventually, some of them are carried back up into the cloud layer by rising air currents. When they encounter conditions suitable for metabolism again, the right temperature, the right chemistry, sufficient water in the acid droplets, they rehydrate, activate, and resume their active phase. In this model, Venus's atmosphere is not a static habitat, but a cycling one, and Venusian life has evolved to cycle with it. The microbes ride up and down through the atmosphere, active in the clouds, dormant below, active again when they return to the clouds. Their entire existence is bound up with the vertical circulation of Venus's air. There is a precedent for this on Earth. Certain bacteria and fungi can produce spores that survive extreme conditions for years or decades, then reactivate when conditions improve. Anthrax spores can survive for 100 years in soil. Some bacterial spores discovered in ancient amber have been claimed to survive for millions of years, though these claims are contested. The point is that Earth life has developed the trick of switching between active and dormant forms in response to environmental stress. Venusian life could plausibly have taken this trick to an extreme, making the switch a fundamental part of its life cycle rather than an emergency response. What Venusian microbes would look like. If Venusian cloud microbes exist, what would we actually see if we brought a sample back and looked at it under a microscope? They would probably be small. Earth microbes range from about 0.2 micrometers to 10 micrometers in diameter. Venusian cloud microbes would probably be at the smaller end of this range because they would need to remain suspended in atmospheric droplets, and larger particles fall out of the air more quickly. They would probably be roughly spherical because spherical shapes are most efficient for maintaining a protective envelope in a hostile fluid environment. Earth microbes come in many shapes: rods, spirals, chains, filaments. But many of these shapes are adaptations to substrates and surfaces. In a purely fluid environment like Venus's clouds, sphericity is favored. They would probably be colored. This is a somewhat speculative claim, but it has some basis. Venus's clouds contain unidentified ultraviolet absorbers that create the dark markings visible in UV photographs. If these absorbers are biological, a possibility that has been seriously proposed, then Venusian microbes would be producing pigments that absorb ultraviolet light, presumably either for photosynthesis, using UV as an energy source, or for protection, blocking UV from damaging their internal chemistry. Either way, they would be colored, probably in shades of yellow, orange, or brown. Their internal structure would be strange to us. If they use sulfuric acid biochemistry, they would have no water-based cellular components, no organelles as we understand them, no aqueous cytoplasm, no water-loving membranes. Instead, their interiors would be organized around acid-tolerant structures, potentially containing significant amounts of sulfur, oxidized carbon compounds, and possibly small amounts of silicon or other elements that Earth life uses only sparingly. They would probably not have DNA. DNA is stable in water but is destroyed by concentrated sulfuric acid. If Venusian life stores genetic information, it uses some other polymer for the purpose, perhaps something based on the same acid-stable chemistry as its structural molecules, perhaps something entirely novel. If we found such organisms and studied them, we would learn things about biology that we have literally no other way to learn. Every alternative biochemistry we can currently imagine is, by definition, imagined. It has never been observed. It might not work in practice, even if the chemistry seems plausible on paper. Real Venusian life, if it exists, would show us how a completely independent origin of life actually plays out. What kinds of chemistry evolution actually selects for when it starts from different initial conditions? Ancient surface life. Fossils of the wet era. There is one other possibility for Venusian life that I want to mention, though it is even more speculative than cloud life. If Venus had oceans for billions of years, and if life arose in those oceans, then Venus's ancient surface would have hosted a full biosphere. Not clouds full of exotic microbes, but a normal Earth-like planet with water and sunlight, and the same kinds of biology that developed here. That ancient biosphere is gone. When Venus's oceans evaporated and the planet transitioned to its current state, surface life would have been destroyed completely. The runaway greenhouse would have cooked everything. There is no chance that macroscopic ancient Venusian life survives today. But there might be fossils. If Venus had life for 1 billion years or more, that life would have interacted with the surface. Microbes would have produced sedimentary structures, stromatolites, biofilm-derived textures that could potentially be preserved in ancient rocks. Larger organisms, if they existed, would have produced shells or skeletons that could fossilize. Chemical biosignatures, isotopic ratios in rocks that indicate biological processing, could persist in Venus's tesserae, the ancient highland regions that appear to be the oldest surviving parts of the planet's surface. If we ever land on a tessera region and analyze its rocks in detail, we might find such fossils. Not fresh biology, but preserved evidence of biology that lived billions of years ago in a Venus that no longer exists. The equivalent of the Precambrian fossils on Earth, traces of ancient microbial, mats, and biochemical processes locked into rocks that have been baked and pressurized but not necessarily destroyed. This is one of the reasons Da Vinci is targeting Alpha Regio, a tessera region, not because we expect to find dinosaur bones, but because if there is any evidence of ancient Venusian life still preserved anywhere on the planet, the tesserae are the most likely place to find it. The philosophical implication of finding such fossils would be enormous. It would mean that life arose on 2 adjacent planets in our solar system, developed independently, and one of them died. The universe would suddenly look very different. A place where life is not rare but common, and where the persistence of life is more contingent than its origin. The bottom line on Venusian life. Let me be honest about where the scientific consensus actually stands as of 2026. The consensus is, we don't know. Most astrobiologists think Venusian cloud life is unlikely but not impossible. The chemistry is challenging. The environment is extreme. The theoretical arguments for how life could survive in concentrated sulfuric acid clouds are speculative and unproven. The phosphan detection which triggered the current wave of interest remains controversial and possibly artifactual. But most astrobiologists also acknowledge that the possibility cannot be ruled out with current data. Venus's cloud chemistry has anomalies that we cannot fully explain. The planet had a habitable past. Life is a persistent phenomenon that, once it arises, tends to survive in surprising places. If Venusian life exists, it would be one of the most important discoveries in the history of science, and the cost of not looking is too high to accept. So the missions are being planned, the probes are being built. In the next decade or so, we will begin to get real data, direct measurements of Venus's cloud chemistry, samples analyzed for organic compounds, high-resolution surveys of the surface for evidence of ancient biosignatures. We may find nothing, and Venus will settle into its identity as a purely dead world. Or we may find something, and everything we thought we knew about life in the universe will have to be rewritten. Both outcomes would be scientifically valuable. Both would tell us important things. The question is, which one is true? And we are finally in a position to try to find out. Could Earth become Venus? This is the question that makes Venus urgent rather than merely fascinating. Everything I have described so far, the temperature, the pressure, the acid, the dead surface, the runaway history, is scientifically interesting on its own terms. But the reason Venus commands so much public attention, and the reason it appears so often in discussions of climate policy and planetary futures, is that Venus is a warning. Venus shows us what can happen to a rocky planet under certain conditions. The question is, are those conditions ones that Earth could experience? Let me answer this carefully, because there is a lot of confusion in popular discussions of this topic. There are people who believe that Earth is about to become Venus imminently, and there are people who believe it is chemically impossible for Earth to ever become like Venus, and both of these views are wrong. The reality is more nuanced and honestly more interesting than either extreme. The runaway greenhouse effect. The mechanism that transformed Venus is called the runaway greenhouse effect, and it works like this. A planet's temperature is determined by the balance between energy coming in, sunlight, and energy leaving, infrared radiation emitted back into space. If more energy comes in than leaves, the planet warms. If more leaves than comes in, it cools. Under normal conditions, this balance stabilizes at some equilibrium temperature that depends on the planet's distance from its star, its atmospheric composition, its reflectivity, and various other factors. Greenhouse gases, water vapor, carbon dioxide, methane, and others, reduce the amount of infrared radiation that can escape a planet's atmosphere. They absorb outgoing infrared, then re-emit it in random directions, including back toward the surface. This keeps a planet warmer than it would otherwise be. Earth is about 33 degrees Celsius warmer than it would be without its natural greenhouse effect. This is a good thing. Without greenhouse gases, Earth would be a frozen ball. But greenhouse gases can create a feedback loop, particularly water vapor. As a planet warms, more water evaporates from its oceans. Water vapor is itself a greenhouse gas, so more water vapor in the atmosphere causes more warming, which causes more evaporation, which causes more warming. Under most conditions, this feedback loop is limited. As the atmosphere warms, it also radiates more infrared into space, and eventually a new equilibrium is reached at a higher temperature. But if the incoming solar energy exceeds a critical threshold, the water vapor feedback becomes unstable. The atmosphere can no longer radiate infrared efficiently enough to keep up with the warming because the water vapor itself is trapping so much of the infrared radiation. The oceans evaporate completely. Once all the water is in the atmosphere as vapor, the atmosphere becomes extraordinarily opaque to infrared radiation, and the surface temperature rises to enormous values, potentially high enough to melt rock. In the process, water vapor rises to the upper atmosphere where ultraviolet radiation from the sun dissociates it into hydrogen and oxygen, and the light hydrogen escapes to space, permanently removing water from the planet. This is what happened to Venus. Its proximity to the sun meant that solar heating exceeded the critical threshold for stable water vapor in the atmosphere. The oceans evaporated. The water was lost to space. The atmosphere filled with carbon dioxide released from the crust. Because normally, on a wet planet, CO2 dissolves in ocean water and gets incorporated into carbonate rocks. But with no oceans, this carbon sequestration cannot happen. The atmosphere thickened with CO2. The greenhouse effect intensified. Temperatures climbed to their current apocalyptic values. The question for Earth is, could this happen to us? The short answer is yes, but not from human activity, and not soon. Let me expand. The sun is slowly getting brighter. The sun, like all main sequence stars, is slowly increasing its luminosity over time. This is a consequence of stellar evolution. As the sun ages, it converts hydrogen to helium in its core, and the resulting changes in core composition and temperature cause the sun to become progressively brighter and slightly hotter over billions of years. Right now, the sun is about 30% brighter than it was when it formed 4.6 billion years ago. It will continue to brighten. In roughly 1 billion years, the sun will be about 10% brighter than it is today. In 2 billion years, roughly 20% brighter. In 5 billion years, the sun will begin to leave the main sequence entirely, expanding into a red giant that will engulf the inner planets. Long before the red giant phase, however, the sun's increasing brightness will push Earth across the runaway greenhouse threshold. Climate models suggest that Earth's oceans will begin to evaporate uncontrollably somewhere between 500 million and 1.5 billion years from now, when the sun becomes bright enough that Earth crosses into the inner habitable zone boundary, the same boundary that Venus is on the wrong side of today. When this happens, Earth will go through the same process Venus did. The oceans will evaporate. The water will be lost to space. The atmosphere will thicken with released CO2. Surface temperatures will climb. Earth will become a version of Venus. This is not a hypothetical. This is a scheduled event in Earth's future. Assuming nothing dramatic changes, no massive stellar disruption, no engineering scale intervention by whatever civilization exists at that time, Earth will become Venus-like in roughly 1 billion years, give or take. That is a long time from now. It is longer than complex life has existed on Earth. There is no reason for any currently living person to worry about this on any personal or civilizational timescale, but it is a real fact about Earth's future, and it means that Venus's fate is, in the very long run, our fate too. The question is only when, not whether. Human-caused climate change cannot produce a runaway greenhouse. Now let me address the more immediate question, because this is where a lot of public confusion exists. Human-caused climate change is a serious, real, urgent problem. The burning of fossil fuels has increased atmospheric CO to concentrations from around 280 parts per million before the Industrial Revolution to over 420 parts per million today. Global average temperatures have risen by about 1.2 degrees Celsius over the same period. Sea levels are rising, ice sheets are melting, weather patterns are changing, ecosystems are being disrupted. If current trends continue, the consequences for human civilization and for the biosphere will be severe. But human-caused climate change cannot by itself trigger a runaway greenhouse effect that turns Earth into Venus. This is worth being clear about because the claim is sometimes made in popular discussions, and it is not scientifically correct. The reason is that Earth is not currently close to the runaway greenhouse threshold. The solar energy flux at Earth's orbit is well below the critical value at which water vapor feedback becomes unstable. Even if human activity added enormous amounts of CO2 to the atmosphere, far more than any realistic emission scenario, the resulting temperature increase would not push Earth across the runaway threshold. There is a significant margin of safety provided by the fact that we are 30% farther from the Sun than Venus is. Detailed climate models have addressed this question directly. They find that even burning every accessible fossil fuel reserve on Earth, coal, oil, natural gas, methane, clathrates, all of it would raise atmospheric CO2 to something like 5,000 parts per million at maximum. This would produce catastrophic warming, probably 8 degrees Celsius to 12 degrees Celsius above pre-industrial temperatures, which would be devastating for human civilization and would kill a large fraction of Earth's species. But it would not evaporate the oceans. It would not initiate a runaway greenhouse. Earth would settle into a hot, hostile, but still recognizable state, with liquid water still present at the surface, though under very different conditions from today. So the correct framing is this: human-caused climate change is a civilization-threatening problem that requires urgent action. It is not, however, a planet-killing threat in the Venus sense. Earth's fate as a habitable world is not in immediate danger from human emissions. What is in danger is human civilization and the specific ecosystems and species that depend on the climate patterns that have prevailed during human evolution. This distinction matters. If people believe that climate change will turn Earth into Venus, they may either A, panic and give up, believing that all is lost, or B, dismiss the concern as obviously exaggerated when they learn the true physics. Both responses undermine the actual work of addressing climate change, which is serious enough on its own terms without needing to be inflated into a Venus-style apocalypse. What would it take to actually turn Earth into Venus? Since the question is inherently interesting, let me address it seriously. What would it actually take to turn Earth into a Venus-like planet? The simplest answer is significantly more solar energy. If you moved Earth closer to the Sun, say to Venus's orbit at 0.72 astronomical units, Earth would undergo a runaway greenhouse effect within thousands of years. The oceans would evaporate. The water would escape to space. The atmosphere would fill with CO2. Earth would become Venus. Short of moving the planet, there are various theoretical mechanisms that could trigger a runaway greenhouse, but all of them require energy inputs far beyond anything humans are capable of producing. You could increase the sun's brightness by 10% or more. This will happen naturally in about 1 billion years, but no human technology can affect stellar output. You could inject enormous quantities of greenhouse gases into the atmosphere, not the tens of gigatons per year that human activity currently produces, but tens of thousands of gigatons, released quickly enough to overwhelm all the natural carbon cycling mechanisms. This would require industrial activity on a scale thousands of times larger than the current global economy. You could destroy Earth's ozone layer completely and expose the surface to unfiltered ultraviolet radiation, which would break down water in the upper atmosphere and enhance hydrogen escape. This would accelerate water loss, but not necessarily trigger a full runaway. You could add enormous amounts of dark material to Earth's surface or atmosphere, reducing the planet's reflectivity and increasing absorbed solar energy. Doing this at planetary scale is far beyond current capabilities. You could impact Earth with a very large asteroid or comet, large enough to vaporize the oceans and inject enormous amounts of water, vapor, and CO2 into the atmosphere simultaneously, An impact of the required size would probably kill everything on Earth's surface, regardless of climate effects. But if the planet had time to recover, the resulting atmospheric composition might, in principle, be pushed toward a Venus-like state. The impact that killed the dinosaurs was nowhere near this scale. None of these scenarios are things that could plausibly happen through normal human activity. The runaway greenhouse threshold is set by solar physics, not by industrial policy. Earth is protected from Venus's fate by its distance from the sun. The wet greenhouse and the moist greenhouse. To be complete, I should mention that there are intermediate states between normal Earth and Venus that Earth could conceivably reach through more dramatic warming. Climate scientists sometimes distinguish between the full runaway greenhouse, which requires solar flux to exceed a critical value, and the moist greenhouse or wet greenhouse state. In a moist greenhouse, the atmosphere becomes water vapor rich, but does not fully evaporate the oceans. Instead, the upper atmosphere becomes wet enough that water reaches the stratosphere in large quantities, where it is photodissociated by UV light. Over millions of years, hydrogen escape gradually removes Earth's water, even without full ocean evaporation. This is a slower version of Venus's fate, but it produces essentially the same end state: a dry planet with a thick CO2 atmosphere. The moist greenhouse threshold is somewhat lower than the full runaway threshold. Some models suggest that Earth could enter a moist greenhouse state with less extreme forcing than a full runaway would require. However, even the moist greenhouse threshold is significantly above current conditions, and probably above conditions producible by any realistic human emission scenario. The point is, the transition from Earth to Venus is not a single sharp threshold, but a series of increasingly severe states. The good news is that we are far from all of them. The bad news is that the severe states between current Earth and full Venus are still catastrophic. We do not need to turn Earth into Venus for climate change to be disastrous. We only need to warm the current climate by a few degrees, which is more than sufficient to cause enormous damage without transforming the planet into a hellscape. The deeper lesson. I want to end this section with what I think is the deeper lesson of the Venus-Earth comparison. The lesson is not, Earth is about to become Venus. That is not true, and it is not the point. The lesson is that planetary climates are not stable in the naive sense. They are stable within certain ranges, and they exhibit strong feedback effects when pushed outside those ranges. Small changes in initial conditions can produce enormously different outcomes over long timescales. Venus and Earth started nearly identical, and one small difference, being 30% closer to the Sun, cascaded through billions of years of amplifying feedbacks until the two planets became almost as different as rocky worlds can be. This means that Earth's climate is a system with tipping points, some of which we understand and some of which we don't. The current human-caused warming is unlikely to trigger a Venus-style runaway, but it may trigger smaller, less dramatic tipping points. The collapse of major ice sheets, the destabilization of the Amazon rainforest, the shutdown of ocean circulation patterns, the release of Arctic permafrost carbon. Each of these is a system that has stability under current conditions, but that could shift into a very different state under sufficient forcing. Each represents a potential feedback that could accelerate warming beyond what direct human emissions would produce. The lesson from Venus is not that Earth is about to boil. The lesson is that planetary systems are more capable of dramatic change than they look, that stability is a range rather than an absolute, and that the transitions between stable states can be irreversible. Venus is not our immediate future. But Venus reminds us that our long-term future includes the possibility of dramatic change, and that we should not assume Earth's habitability is guaranteed. Habitability is a condition that exists within a set of physical constraints, and those constraints are not infinitely flexible. Push hard enough in the right direction for long enough, and any planet, including this one, can shift into a state that we would not recognize and could not survive. Take care of Earth. It is the only planet in the solar system where a person can walk outside without a spacesuit and be more or less fine. Venus tells us how narrow that window of habitability actually is, and how easily a planet can slip out of it and never come back. Earth is not Venus, but Earth is in the same solar system as Venus, made of the same materials, subject to the same underlying physics. The differences between the two are not differences of kind, but differences of degree, of position, of accumulated feedback over billions of years. And degrees, positions, and feedbacks are things that can, in principle, change. Venus is what our sister world looks like now. Earth is what our sister world could have been, and what our world still is. Whether Earth remains recognizable as Earth for the next 1,000 years, or the next 10,000, or the next million, depends in part on choices being made now, by us, in factories and legislatures and boardrooms across a planet that most people never think about as a planet at all. Venus is watching us in a way. Not literally. Venus is a rock in space. It doesn't watch anything. But the fact of Venus, the existence of Venus, the presence of that hellish twin world just next door in the solar system is a kind of watching. It is a permanent, silent, planetary scale reminder that things can go wrong, that planets can die, that our world is not automatically or eternally the way it is now. We are a species that evolved on a planet with an unusually stable climate over the past 10,000 years, the entire span of human civilization. We tend to think of Earth's conditions as fixed, as given, as the natural background against which our lives take place. Venus tells us that this is wrong. Earth's conditions are the outcome of a long, contingent, feedback-driven process, and other outcomes were and are possible. The Venus we see tonight in the western sky, brilliant and beautiful and utterly deadly, is one of those other outcomes. It is what happened next door. It is a completed experiment in what a rocky planet can be if things go wrong. We have the enormous privilege of being able to look at that experiment from a safe distance on a planet where things went right, and to learn from it. Whether we do learn from it, whether we take the lesson seriously enough to protect the fragile, contingent, precious habitability of our own world, is up to us. Venus can't tell us the answer. Venus can only be what it is: a warning in the sky, a mirror in the twilight, a sister that shows us what we might have been, and what we might still, in some far future, become. Look up tonight. If Venus is in the sky, find it. Let it be beautiful to you. Let it be terrible to you. Let it be both at once, because it is both at once. And then look around at the world you actually live on. The trees, the water, the sky that is blue rather than yellow-orange, the air that is breathable rather than lethal, the ground that supports life rather than melting lead. Notice that this is not a given. Notice that this is the outcome of a very long story that could have gone otherwise and that continues to be written. Venus is our warning. Earth is our home. The distance between the two is smaller than it looks and larger than it needs to be, and exactly as large as